Welcome, fellow dreamer. Tonight, we journey beyond our world to explore the story of satellites, those remarkable companions circling silently above us, transforming how we communicate, navigate, and understand both Earth and the cosmos. This tale unfolds alongside soothing music and abstract imagery, revealing little-known wonders and fascinating stories that will gently feed your curiosity as you drift towards sleep. So take a deep breath, settle into comfort, and let your mind and eyes rest as the story begins. Long before any human-made object circled our world, people gazed upward and wondered. The night sky, scattered with stars and graced by the moon's steady orbit, inspired countless questions across generations. Ancient astronomers tracked celestial movements with remarkable precision, noting how the moon traced its path around Earth with predictable regularity. They observed the planets wandering against the backdrop of fixed stars. And in these natural rhythms, some began to imagine what else might be possible above our heads. The concept of objects circling Earth didn't spring suddenly into existence. It grew gradually, nurtured by advancing understanding of gravity, motion, and the mechanics of the heavens. When Isaac Newton described the laws governing how objects move and how gravity pulls them together, he planted intellectual seeds that would eventually flower into practical possibilities. In his writings, Newton posed a thought experiment about a cannon on a mountaintop firing a projectile with ever-increasing force. Fire it gently, and the ball falls to Earth nearby. Fire it harder, and it travels farther before landing. But fire it with sufficient speed, Newton reasoned, and the projectile would fall around the Earth rather than into it, perpetually circling in what we now call orbit. This mathematical exercise existed purely in imagination during Newton's lifetime, but the principle was sound. As the 19th century unfolded, writers of fiction began exploring possibilities that science had hinted at but couldn't yet achieve. These storytellers served as bridges between mathematical theory and public imagination, translating abstract concepts into vivid narratives that captured people's fascination. Their visions, though sometimes fanciful in detail, asked serious questions about humanity's relationship with the space surrounding our planet. Jules Verne, the French novelist whose works helped define science fiction as a genre, wove space travel into several of his stories. His 1865 novel, From the Earth to the Moon, imagined a projectile fired toward the lunar surface, carrying passengers on an unprecedented journey. While Verne's propulsion method wouldn't have worked in reality, his attention to certain scientific principles and his enthusiasm for technological possibility inspired readers to consider space as a destination rather than merely a mystery to observe from afar. Verne's stories reached audiences across continents, translated into numerous languages, sparking conversations about whether such adventures might someday move from fiction to fact. Around the same time, an American clergyman and writer named Edward Everett Hale published a story that came remarkably close to describing an artificial satellite. His 1869 tale, The Brick Moon, imagined a large sphere constructed from bricks, intended to be launched into orbit around Earth to serve as a navigation aid for ships at sea. In Hale's story, this artificial moon would circle the planet at a constant position in the sky, providing mariners with a fixed reference point. Though his launching method was purely fantastical, involving massive flywheels, Hale had grasped something profound. He understood that a human-made object could theoretically orbit Earth, just as the natural moon does, and he imagined practical purposes such an object might serve. His brick moon would help people navigate, communicate, and observe from above, functions that real satellites would indeed fulfill a century later. These fictional explorations occurred during an era of rapid technological advancement. Railways connected distant cities. Telegraph wires carried messages across continents, and steamships conquered oceans with increasing reliability. Each breakthrough made previously impossible tasks routine, encouraging people to dream bigger. If humans could communicate instantly across thousands of miles using electrical signals, might they someday place observation posts in the sky itself? If balloons could lift people above the clouds, might other methods eventually carry objects higher still? The late 19th and early 20th centuries saw growing scientific understanding of Earth's atmosphere and the space beyond it. Researchers using balloons and mountain observatories discovered that air grows thinner with altitude, eventually giving way to the near vacuum of space. This knowledge posed both challenges and opportunities for anyone imagining artificial satellites. Objects in space wouldn't need to fight atmospheric resistance, but reaching that environment would require overcoming gravity's strong pull and pushing through the atmosphere's layers, a task demanding power sources and technologies that didn't yet exist. Russian schoolteacher Konstantin Tsiolkovsky, working in relative isolation, began applying rigorous mathematics to spaceflight concepts in the 1890s and early 1900s. He calculated the velocities needed to reach orbit and recognized that liquid-fueled rockets offered the most promising path to space. Tsiolkovsky understood that an artificial satellite would need to achieve tremendous speed to balance gravity's pull with centrifugal force, creating stable orbit. His theoretical work remained largely unknown outside Russia during his lifetime, but he had begun translating imaginative fiction into mathematical blueprints. Across the Atlantic, American physicist Robert Goddard independently reached similar conclusions about rockets and spaceflight. Goddard went beyond theory to build and test actual rockets, though his early experiments were small-scale and often frustrated by technical difficulties. He envisioned rockets carrying instruments high into the atmosphere and potentially beyond, writing about artificial satellites in his private notes, even when public discussion of such ideas invited ridicule. The dreamers and theorists of the 19th and early 20th centuries created foundations for what would eventually become reality. Science fiction writers gave the public vocabulary and vision for satellites, making the concept familiar and desirable. Mathematicians and physicists developed the equations describing orbital mechanics and the energy requirements for reaching space. Early rocket experimenters began the practical work of building vehicles that might someday achieve the necessary speeds. These pioneers worked largely in isolation from one another, separated by geography, language, and the slow pace of information sharing in their era. Yet, they were united by a common fascination with the space above Earth and the possibilities it held. They looked at the moon's faithful orbit and asked why humanity couldn't place its own objects in similar paths. They imagined these artificial moons serving practical purposes: navigation aids, observation platforms, and communication relays, functions that proved remarkably prescient. The dreams took shape slowly. accumulating over decades as technology gradually caught up with imagination. Each advance in rocketry, each refinement in understanding orbital mechanics, each story capturing public imagination brought artificial satellites closer to reality. The transition from fantasy to engineering project would require particular circumstances: geopolitical competition, military interest, and concentrated resources. But the essential vision had already been established by those who dared to imagine objects circling Earth above the atmosphere, serving humanity's needs while demonstrating what ingenuity might accomplish when directed skyward. The dreamers of the 19th century had imagined artificial moons circling Earth, but their visions remained bound to the page, constrained by the simple reality that humanity possessed no means to lift anything beyond the atmosphere. The early 20th century would change this limitation forever, as a handful of visionaries began working with a technology that seemed almost absurdly simple in principle, yet devastatingly difficult in practice: the rocket. In the quiet isolation of a small Russian town, a self-taught schoolteacher named Konstantin Tsiolkovsky spent his evenings filling notebooks with mathematical equations. Born in 1857, he had lost much of his hearing to scarlet fever as a child, which drove him into books and solitary contemplation. By the 1880s and 1890s, his thoughts had turned skyward. While others viewed rockets as little more than fireworks or weapons, Tsiolkovsky perceived something revolutionary. He understood that in the vacuum of space, where nothing existed to push against, the rocket's principle of action and reaction offered the only viable means of propulsion. In 1903, the same year the Wright brothers achieved powered flight at Kitty Hawk, Tsiolkovsky published his landmark paper, exploring the mathematics of rocket flight. He derived what became known as the rocket equation, a fundamental relationship showing how the velocity a rocket could achieve depended on the speed of its exhaust gases and the ratio between its full and empty mass. This elegant mathematical framework revealed both the promise and the challenge of space travel. To reach orbital velocities, a rocket would need to carry enormous quantities of fuel relative to its payload, burning through its propellant with fierce intensity. Tsiolkovsky proposed using liquid fuels rather than solid powders, recognizing that liquids could be controlled more precisely and would burn more efficiently. He envisioned multi-stage rockets that would shed empty fuel tanks as they climbed, reducing dead weight. He even sketched designs for space stations and imagined humans living beyond Earth's atmosphere. Yet Tsiolkovsky built nothing. His contributions remained theoretical, mathematical proofs that spaceflight was possible according to the laws of physics, even if the engineering challenges seemed insurmountable. Across the Atlantic Ocean, another quiet innovator was moving from theory toward practice. Robert Goddard, born in Massachusetts in 1882, had been captivated by space travel since his youth. On October the 19th, 1899, while climbing a cherry tree to prune branches on his family's farm, the 17-year-old Goddard looked up at the sky and experienced what he later described as a vision of a device that might reach Mars. This moment became so significant to him that he celebrated it privately each year as his anniversary day. Goddard pursued physics, earning his doctorate and eventually joining the faculty at Clark University. Unlike Tsiolkovsky, he was determined to build actual hardware. Working with meticulous care in his workshop, he conducted hundreds of experiments testing different propellants, nozzle designs, and cooling systems. He too recognized the superiority of liquid fuels, particularly liquid oxygen combined with gasoline or other hydrocarbons. The challenge lay in controlling these volatile substances, pumping them into a combustion chamber where they would ignite with tremendous force, producing exhaust velocities far exceeding anything possible with solid fuels. On March 16, 1926, in a snow-covered field on his aunt's farm in Auburn, Massachusetts, Goddard achieved something unprecedented. His liquid-fueled rocket, standing just 10 feet tall and looking almost comically fragile with its exposed framework, ignited and rose into the cold air. The flight lasted only 2.5 seconds, reaching an altitude of 41 feet before arcing over and landing in a frozen cabbage patch some distance away. By the standards of later rocketry, it was barely a hop, yet it represented the first controlled flight of a liquid propellant rocket, the ancestor of every rocket that would eventually carry satellites into orbit. Goddard continued his experiments throughout the 1920s and 1930s, moving his work to New Mexico, where the open spaces and cooperative weather provided better conditions. His rockets grew larger and more sophisticated, incorporating gyroscopic stabilization systems, parachute recovery mechanisms, and improved fuel pumps. He received some support from the Smithsonian Institution and later from the Guggenheim family, but he worked largely in isolation, protective of his designs and wary of sharing details that others might exploit. Meanwhile, in Germany, enthusiasm for rocketry was taking a different path. Amateur rocket societies attracted engineers and dreamers who shared Tsiolkovsky's and Goddard's visions. The Verein für Raumschifffahrt, or Society for Space Travel, conducted public demonstrations of their experimental rockets through the late 1920s and early 1930s. Among the young enthusiasts attending these demonstrations was Wernher von Braun, a teenager from an aristocratic Prussian family who would become perhaps the most consequential rocket engineer of the 20th century. As Germany's political situation darkened in the 1930s, the military took interest in rocket development. The army established a research program at Peenemünde, a remote site on the Baltic coast, and recruited von Braun and other talented engineers. Over the next decade, these teams developed increasingly powerful rockets, culminating in the V-2, which stood 46 feet tall and could carry a 1-ton warhead across distances exceeding 200 miles, reaching altitudes above 60 miles before descending on its target. The V-2 represented a tremendous, though troubling, achievement. It was the first human-made object to reach the edge of space, powered by liquid oxygen and alcohol burning in a sophisticated engine that generated some 56,000 pounds of thrust. Its guidance system, though primitive by later standards, demonstrated that rockets could be steered and controlled during flight. The technical knowledge embodied in the V-2 would prove invaluable for future space exploration, even though its wartime use brought destruction and suffering. When the war ended in 1945, both American and Soviet forces raced to capture German rocket technology and personnel. Teams of engineers, including von Braun and many of his colleagues, were brought to the United States, while the Soviet Union secured other engineers and substantial quantities of V-2 hardware and documentation. Both nations began intensive programs to understand, replicate, and improve upon German rocket designs. In the American Southwest, captured V-2 rockets were launched on research missions, carrying scientific instruments to the upper atmosphere to measure cosmic rays, solar radiation, and atmospheric conditions. These flights demonstrated that rockets could serve peaceful scientific purposes, carrying payloads beyond the reach of aircraft or balloons, and returning data from the threshold of space. The Soviet Union pursued parallel efforts, and under the direction of Sergei Korolev, a brilliant engineer who had survived imprisonment during Stalin's purges, Soviet teams rapidly advanced beyond captured German technology to develop their own powerful rockets. By the early 1950s, both nations were designing ballistic missiles capable of crossing continents. And these same rockets, built initially for military purposes, possess the power necessary to place objects into orbit around Earth. The theoretical foundations laid by Tsiolkovsky, the practical demonstrations conducted by Goddard, and the engineering advances forced by wartime urgency had converged to create a capability that previous generations could only imagine. Rockets, powerful enough to escape Earth's gravitational embrace, existed, and the engineers who understood how to build and control them were refining their designs with each test flight. The dreams of artificial moons, once confined to fiction and mathematical speculation, stood on the verge of reality as the world moved toward a decade that would witness humanity's first reach beyond the planet. The world that emerged from the devastation of World War II was fundamentally different from the one that had entered it. Nations that had been allies in conflict now found themselves separated by deep ideological divides, their wartime cooperation giving way to suspicion and competition. In this transformed landscape, the dreams of spaceflight and artificial satellites acquired new urgency, no longer purely the province of visionaries and scientists, but increasingly matters of national prestige and strategic importance. By the early 1950s, both the United States and the Soviet Union had assembled teams of rocket scientists and engineers, many of them drawn from the German rocket program that had created the V-2. These specialists found themselves working in very different environments, separated by what had come to be called the Iron Curtain, yet pursuing remarkably similar goals. The theoretical knowledge of how to reach space existed. The question was which nation would transform that knowledge into reality first. In the Soviet Union, a brilliant engineer named Sergei Korolev led the effort to develop increasingly powerful rockets. Korolev had survived imprisonment during Stalin's purges and emerged with his passion for spaceflight intact. Working in conditions of absolute secrecy, known to the outside world only as the chief designer, he oversaw the development of rockets that officially served as delivery systems for weapons, but which he envisioned using for peaceful space exploration. His teams worked at facilities in remote areas, their progress unknown to Western observers. Meanwhile, in the United States, rocket development proceeded along multiple paths. The Army, Navy, and Air Force each pursued their own programs, sometimes competing with one another as much as with external adversaries. Werner von Braun, now working for the US Army at the Redstone Arsenal in Alabama, continued to advocate for spaceflight while developing military rockets. He published articles in popular magazines, collaborated on a series of television programs about space exploration, and never missed an opportunity to promote the idea of launching satellites. The scientific community in both nations recognized that satellites could serve purposes beyond military applications, Scientists understood that instruments placed above the atmosphere could observe cosmic rays, solar radiation, and other phenomena that Earth's protective blanket of air made difficult to study from the ground. Meteorologists imagined cameras that could photograph weather systems from above. Communication engineers considered how satellites might relay radio signals across vast distances. In 1952, the International Council of Scientific Unions began planning an ambitious worldwide research effort called the International Geophysical Year. Despite Cold War tensions, scientists from 67 nations agreed to cooperate in studying Earth's physical properties during an 18-month period from July 1957 to December 1958. This period was chosen because it coincided with a time of maximum solar activity, offering unique opportunities for observation. As plans for the International Geophysical Year developed, both American and Soviet scientists proposed including artificial satellites in the research effort. A satellite orbiting Earth could gather data impossible to obtain any other way, studying the upper atmosphere, cosmic radiation, and the space environment surrounding the planet. The concept appealed to the international scientific community, representing exactly the kind of cooperative research the Geophysical Year was meant to foster. In July 1955, the United States officially announced its intention to launch a small satellite as part of its contribution to the International Geophysical Year. The announcement came from the White House itself, lending the project official government backing. The satellite program would be called Vanguard, and it would be developed by the Naval Research Laboratory rather than by Army teams. This decision disappointed von Braun, who felt confident his team could launch a satellite quickly. But the Eisenhower administration preferred to keep the civilian scientific satellite program separate from military rocket development. The Vanguard satellite would be small, weighing only a few pounds, and would carry instruments to study the upper atmosphere and test satellite tracking techniques. The rocket designed to launch it would be developed specifically for peaceful purposes, making clear that America's first satellite served scientific rather than military goals. Teams began working on the complex systems needed, not just to launch a satellite, but to track it once in orbit and receive data from its instruments. What Western scientists did not know was that Soviet teams were pursuing their own satellite plans with characteristic secrecy. The Soviet Union had made no public announcement of satellite intentions, but Korolev had received approval to develop a spacecraft that could orbit Earth. The Soviet satellite program proceeded quietly, with progress known only to those directly involved and the political leadership that authorized it. By 1956, both programs were advancing, though along different paths. The American Vanguard project proceeded methodically, with careful attention to developing new technologies and ensuring that every system met rigorous standards. Test launches of early Vanguard rockets showed progress, but also revealed technical challenges that required additional time to resolve. The scientists and engineers working on Vanguard expected to have their satellite ready sometime in 1958, comfortably within the International Geophysical Year timeline. The Soviet program moved faster, driven partly by Korolev's urgency and partly by a different approach to acceptable risk. Rather than developing entirely new systems, Soviet designers adapted existing military rocket technology for satellite launch. Korolev's teams worked intensively, accepting that their first satellite might be simple in design, if that meant getting it into orbit sooner. As 1957 began, both American and Soviet teams intensified their efforts. In the United States, test launches continued, some successful, and others revealing problems that needed correction. Progress reports appeared in newspapers, and the public began to anticipate America's entry into the space age. Scientists prepared instruments and tracking stations, making ready for the moment when Vanguard would finally carry its small satellite above the atmosphere. In the Soviet Union, preparations proceeded invisibly to outside observers. Launch facilities in Kazakhstan saw increasing activity as rockets were tested and systems checked. Korolev and his teams refined their designs, working toward a launch that would announce Soviet capabilities to a surprised world. The stage was set for a transformation in human history, though few people outside the rocket programs realized how close that moment had come. The long theoretical discussions about satellites, the decades of science fiction speculation, the years of rocket development were all converging toward a point when humanity would finally place an artificial object in orbit around Earth. The question was no longer whether it could be done, but who would do it first and what it would mean when they succeeded. The preparations were complete, the teams assembled, and the rockets ready. On both sides of the world, engineers and scientists had worked tirelessly toward launching humanity's first artificial satellite. But in the quiet hours of October 4th, 1957, while many American researchers slept peacefully in their beds, the Soviet Union moved first. At the Baikonur Cosmodrome in Kazakhstan, beneath a sky still holding the last stars of the night, a modified R-7 rocket stood on its launch pad. Attached to its nose sat a polished sphere of aluminum alloy, just 22.5 inches in diameter, weighing 184 pounds. The Soviets called it Prosteyshi Sputnik, or PS-1, meaning simplest satellite. The world would come to know it simply as Sputnik. The satellite itself was elegant in its simplicity. Its aluminum casing consisted of two hemispheres joined together, creating a perfectly smooth sphere that gleamed in the floodlights. 4 long antennas extended backward from one side, like whiskers on a metallic face, each antenna measuring between 7 and 9 feet in length. These antennas would broadcast the satellite's radio signals back to Earth. Inside the pressurized sphere, protected from the vacuum of space, were batteries, a radio transmitter, and a fan to help regulate temperature. That was all. No cameras, no scientific instruments beyond temperature sensors, no complexity beyond what was absolutely necessary to prove that an artificial object could orbit Earth and communicate its presence. At 5 minutes before midnight, Moscow time, the rocket engines ignited. Fire and smoke billowed across the launch complex as the R-7 lifted slowly, then faster, climbing through the atmosphere with its precious cargo. Stage by stage, the rocket accelerated, shedding spent components as it rose higher and faster. Finally, at the precise moment calculated by Soviet engineers, Sputnik separated from its carrier rocket. Momentum carried it forward at 18,000 miles per hour, fast enough to balance Earth's gravitational pull, fast enough to fall around the planet rather than back to its surface. Sputnik had entered orbit. Within minutes, tracking stations in the Soviet Union detected the satellite's radio signal, a simple tone transmitted on 2 frequencies, 20 and 40 megahertz, sent pulses lasting 0.3 of a second, followed by similar pauses. Beep, beep, beep. The sound was methodical, rhythmic, almost like a heartbeat. This artificial moon was announcing its presence to anyone with a radio receiver capable of detecting the right frequency. The Soviet news agency, TASS, released the announcement to the world. As a result of very intensive work by scientific research institutes and design bureaus, the statement read, "The first artificial satellite in the world has been created. On October 4, 1957, this first satellite was successfully launched in the USSR. The reaction was immediate and global. Radio operators around the world turned their antennas skyward, searching for Sputnik's signal. Amateur radio enthusiasts in Europe picked up the beeping within hours. As Earth rotated and Sputnik continued its orbit, crossing overhead every 96 minutes, more and more people heard it. The satellite was visible too, for those who knew when and where to look. Actually, what observers saw was not Sputnik itself, too small and distant to reflect much sunlight, but rather the spent rocket stage that had carried it to orbit, tumbling alongside its creation in a parallel path. In the United States, the news arrived during the day, spreading rapidly through government offices, research centers, and newsrooms. President Eisenhower was attending a dinner at the White House when informed. His press secretary, James Haggerty, released a brief statement acknowledging the achievement, but noting that the United States had never intended to participate in a race for the first satellite. This measured response did little to calm the growing sense of shock and concern among the American public and press. Newspapers the next morning carried headlines in the largest type reserved for only the most significant events. "Soviet fires Earth satellite into space," declared the New York Times. "Sphere tracked in 4 crossings over US." Radio and television broadcasts devoted extensive coverage to analyzing what this meant. Scientists explained orbital mechanics to rapt audiences. Politicians debated implications for national security. Commentators wondered aloud whether America had fallen behind in scientific and technological capability. The concerns went beyond mere national pride. In the context of 1957, with Cold War tensions defining international relations, a satellite represented more than scientific achievement. The same rocket that could place an object in orbit could, with modifications, deliver a warhead across continents. The Soviet Union had demonstrated a capability that carried both peaceful and military implications, and they had demonstrated it first, before the world's eyes. But beyond geopolitics and security concerns, Sputnik sparked something else. Wonder. For the first time in human history, an artificial object circled the Earth. Not a dream, not a story, not a theoretical possibility, but an actual physical object completing an orbit every hour and a half. People gathered in their yards after sunset, looking upward, hoping to glimpse the moving point of light. They listened to those steady beeps on their radios, each pulse a confirmation that humanity had extended its reach beyond the planet's surface. Scientists recognized immediately what this meant for future possibilities. If a simple sphere with a radio transmitter could orbit Earth, then instruments could follow. Cameras could photograph weather patterns and land masses. Telescopes could observe stars without atmospheric interference. Communication signals could be bounced around the globe. The practical applications seemed limitless. Sputnik continued orbiting for 3 weeks until its batteries expired, and its radio fell silent. The satellite itself remained in orbit for 3 months before atmospheric drag gradually lowered its altitude. On January 4th, 1958, it re-entered Earth's atmosphere, burning up over the Caribbean, completing its brief but historic existence. That small sphere, so simple in design and function, had changed everything. It demonstrated that spaceflight was not merely theoretical, but achievable. It showed that the space age had begun, whether the world felt ready or not. And perhaps most importantly, it created an urgency that would drive the next phase of satellite development, as nations and scientists rushed to follow where Sputnik had led, expanding humanity's presence beyond the atmosphere and into the realm where artificial moons would soon become commonplace, each one building upon the legacy of that first steady, beeping sphere. The news of Sputnik's successful orbit spread across America like ripples across a still pond, disturbing the calm certainty that had characterized the nation's technological confidence. In living rooms and laboratories, in Pentagon offices, and university halls, people listened to the steady beep, beep, beep transmitted from the Soviet satellite as it passed overhead. For many Americans, that simple radio signal carried a complex message. The space age had begun, and the United States had not been first. The response was immediate and multifaceted. Politicians demanded action. Scientists doubled their efforts. Engineers worked through nights that blurred into days. The American satellite program, which had been proceeding at a measured pace under the auspices of Project Vanguard, suddenly found itself thrust into an intense spotlight it had never sought. Vanguard, entrusted to the Naval Research Laboratory, had been chosen partly because it was designed as a purely scientific endeavor, separate from military missile programs. This distinction had seemed important before Sputnik. After Sputnik, it seemed like a luxury the nation could no longer afford. The pressure to launch quickly became overwhelming. On December 6, 1957, just 2 months after Sputnik's triumph, a Vanguard rocket stood on its launch pad at Cape Canaveral, a slender white needle pointing toward the sky. Journalists from around the world had gathered to witness what newspapers were calling America's answer to the Soviet achievement. The countdown proceeded smoothly. The engines ignited with a burst of flame. For a brief moment, the rocket began to rise. Then, barely 4 feet above the ground, the Vanguard rocket lost thrust. It settled back onto the launch pad, crumpled, and exploded in a massive fireball. The tiny satellite it carried was thrown clear, landing in nearby bushes, where it lay transmitting its radio signal to no one in particular, a forlorn voice crying out from the scrubland. The disaster was broadcast on television, replayed in newsreels, and discussed in newspapers across the globe. Some foreign press outlets mockingly dubbed the failed satellite Kaputnik and Flopnik. The embarrassment was profound. But while Vanguard struggled, another team had been working with quiet determination. The Army Ballistic Missile Agency in Huntsville, Alabama, housed a group of engineers and scientists led by Werner von Braun, the German rocket pioneer who had come to America after the war. Von Braun's team had been developing the Jupiter C rocket, a modified version of the Redstone missile. They had long believed their rocket could launch a satellite, but had been passed over in favor of Vanguard. Now, In the wake of Vanguard's spectacular failure, they received permission to try. The task of building the satellite itself fell to the Jet Propulsion Laboratory in California. Time was desperately short. The team, led by William Hayward Pickering, worked at a feverish pace to create a satellite that could be ready in weeks rather than months. They designed a slender cylinder, just 80 inches long and 6 inches in diameter, weighing a modest 30 pounds. Within this compact package, they packed cosmic ray detectors, temperature sensors, and instruments designed by James Van Allen of the State University of Iowa to measure radiation in space. The satellite's exterior was wrapped in distinctive stripes, white and dark bands that would help ground observers track its tumbling motion through their telescopes. Unlike Sputnik's smooth sphere, this American satellite had a more complex shape, with flexible whip antennas extending from its body. The entire assembly was mounted atop a fourth stage of the rocket, spinning rapidly to provide stability during its climb through the atmosphere and into orbit. As January 1958 arrived, the launch preparations moved forward with careful deliberation. The team at Cape Canaveral had learned from Vanguard's failure. Every system was checked and rechecked. The rocket stood ready, white against the Florida sky, as the launch window approached. On the evening of January 31st, as darkness settled over the Atlantic coast, the final countdown began. Von Braun and his colleagues waited in a communications room, dependent on reports from the launch site. Pickering and Van Allen stood nearby, representing the satellite and its scientific instruments. The tension in that room was almost tangible, a physical presence among the men who had worked so hard toward this moment. They had one chance. Another failure would be devastating, both personally and nationally. The rocket ignited precisely on schedule, its flame brilliant against the night. Unlike Vanguard's brief and tragic flight, this rocket climbed steadily, rising on a pillar of fire that illuminated the clouds above. It disappeared into the darkness, still climbing, still accelerating. Minutes passed. The upper stages fired in sequence, each one pushing the satellite higher and faster. Then came the long wait for confirmation that the satellite had achieved orbit. The calculations suggested that if everything had worked perfectly, the satellite should begin transmitting as it came within range of receiving stations. The men in that communications room waited, watching clocks, performing mental calculations, hoping. The minutes stretched on. Had something gone wrong? Had they come so close only to fail at the final moment? Then, faint at first, but growing stronger, the signal arrived. Explorer 1 was in orbit. The relief in that room was overwhelming. Von Braun, normally reserved, allowed himself a smile. Pickering felt the tension drain from his shoulders. Van Allen thought of the instruments now sailing through space, gathering data no one had ever collected before. America had its satellite, and the space race had gained a new dimension of competition and achievement. Explorer followed an elliptical path around Earth, swooping as low as 220 miles above the surface and climbing as high as 1,600 miles at its most distant point. This elongated orbit, more extreme than Sputnik's nearly circular path, would prove scientifically fortunate. As the satellite traveled through different altitudes, Van Allen's instruments detected something unexpected and remarkable. The radiation counters aboard Explorer 1 showed puzzling readings. At certain altitudes, they registered high levels of radiation, as expected from cosmic rays. But at other altitudes, the counters seemed to go silent, reading 0. Van Allen, analyzing the data, realized what was happening. The counters weren't reading 0 because there was no radiation. They were overwhelmed, saturated by radiation levels so intense that they exceeded the instrument's ability to measure. Explorer 1 had discovered enormous belts of charged particles trapped by Earth's magnetic field, regions of space where protons and electrons spiraled along magnetic field lines in vast donut-shaped zones surrounding the planet. These radiation belts, which would come to bear Van Allen's name, were the first major scientific discovery of the space age. They revealed that space near Earth was not empty void, but a complex environment shaped by invisible magnetic forces, filled with energetic particles that posed both challenges and opportunities for future space travelers. The success of Explorer 1 did more than restore American confidence. It demonstrated that satellites could be powerful tools for scientific discovery, revealing phenomena that could never be detected from Earth's surface. The space age, begun with Sputnik's simple beep, had quickly evolved into something richer and more complex, a new frontier where human ingenuity could expand the boundaries of knowledge itself. With Explorer 1 successfully in orbit, and both superpowers having placed their mechanical creations in the sky, a natural question arose in the minds of scientists, engineers, and curious citizens alike. How exactly do these satellites remain suspended above Earth? The answer lies not in any mysterious force, but in elegant physics that had been understood, at least theoretically, for centuries. To comprehend the dance of satellites around our planet, we must first journey back to the 17th century and the mind of Isaac Newton. Sitting in his study in England, Newton contemplated the force that pulled an apple to the ground and realized this same force extended far beyond the surface of Earth. In his imagination, he conceived of a cannon placed atop an impossibly tall mountain, high enough to rise above the atmosphere. If this cannon fired a cannonball horizontally with sufficient speed, Newton reasoned, the ball would fall toward Earth, but never quite reach it. The planet's surface would curve away beneath the falling projectile at exactly the same rate the cannonball descended, creating a perpetual state of falling without landing. This thought experiment perfectly describes what we now call orbit. The mathematics of this celestial mechanics reveals precise relationships. To achieve orbit at a particular altitude, a satellite must travel at a specific velocity. Too slow, and gravity wins, pulling the object back to Earth. Too fast, and the satellite escapes Earth's gravitational embrace entirely, wandering into deeper space. The balance point, called orbital velocity, changes depending on altitude. Closer to Earth, where gravitational pull is stronger, satellites must move faster to maintain their circular paths. Further away, where gravity's grip loosens, slower speeds suffice. Consider low Earth orbit, the realm where those first satellites circled. At altitudes between roughly 100 and 1,000 miles above the surface, satellites must race along at approximately 17,000 miles per hour to maintain their paths. At this tremendous speed, a satellite completes one full circuit of Earth in about 90 minutes. experiencing 16 sunrises and sunsets each day. The International Space Station, in our modern era, occupies this region, as did Explorer 1 and countless satellites that followed in those early years. The shape of an orbit need not be perfectly circular. In fact, many early satellites followed elliptical paths, swooping closer to Earth at one point in their orbit, called perigee, and swinging farther away at the opposite point, called apogee. Explorer 1 traced just such an ellipse, its closest approach bringing it within 200 miles of Earth's surface, while its most distant point carried it over 1,500 miles away. These elliptical orbits occur naturally when a satellite's velocity isn't precisely calibrated for a circular path at its injection altitude. As satellite technology matured, engineers discovered they could exploit different orbital altitudes and inclinations for specific purposes. The angle at which a satellite's orbital plane tilts relative to Earth's equator, called inclination, determines which portions of the planet's surface it can observe. A satellite launched due east from the equator maintains zero inclination, circling endlessly above the equatorial regions. Launch it toward one of the poles instead, and the satellite traces a path that carries it over higher latitudes with each orbit. Polar orbits proved particularly valuable for certain applications. A satellite following a path nearly perpendicular to the equator, passing close to both poles, sees different portions of Earth's surface with each successive orbit. As the planet rotates beneath it, the satellite's ground track shifts westward, eventually covering the entire globe. This characteristic makes polar orbits ideal for mapping, surveillance, and monitoring applications where complete planetary coverage matters more than continuous observation of specific locations. At the opposite extreme lies one of the most elegant solutions in orbital mechanics, the geostationary orbit. At an altitude of approximately 22,300 miles above the equator, something remarkable occurs. A satellite orbiting at this specific height travels at exactly the right speed to complete one orbit in precisely 24 hours. Since Earth also rotates once every 24 hours, the satellite appears to hover motionless over a fixed point on the equator. From the ground, such a satellite occupies a permanent position in the sky, simplifying communication tremendously, since antennas can point at a fixed direction rather than tracking a moving target across the heavens. The mathematics that make geostationary orbits possible were understood long before satellites existed. Arthur C. Clarke, the science fiction writer and scientist, published calculations describing this special orbit in 1945, more than a decade before Sputnik. He envisioned a network of 3 communication satellites positioned in geostationary orbit, equally spaced around the equator, providing global coverage. This concept would eventually become reality, though Clarke himself noted he thought satellites would be too expensive to be practical. History proved him wrong about the economics, though his mathematical insights were absolutely correct. Between the extremes of low Earth orbit and geostationary altitude lies medium Earth orbit, a region less densely populated, but useful for specific applications. Satellites placed here orbit every few hours, providing a compromise between the frequent complete coverage of low orbits and the fixed position of geostationary platforms. Understanding orbital mechanics also meant grappling with the reality that no orbit remains perfect indefinitely. Even high above the atmosphere's dense lower layers, satellites encounter wisps of gas molecules, that create tiny amounts of drag. Over time, this friction gradually slows a satellite, causing its orbit to decay. Eventually, without periodic boosts to restore lost velocity, a satellite spirals downward, entering ever denser atmosphere until friction generates heat sufficient to vaporize the craft. Many early satellites met this fate within months or years of launch. The Moon's gravitational influence and the Sun's radiation pressure also perturb satellite orbits in subtle ways. Engineers learn to calculate these effects and either compensate for them with occasional thruster firings or choose orbital parameters that minimize their impact. The precision required to maintain exact orbits, particularly for constellations of satellites that must work in coordination, demands sophisticated calculations and constant monitoring. As understanding of orbital mechanics deepened, mission planners gained the ability to craft orbits tailored to specific needs. They could calculate launch windows when Earth's rotation would carry the launch site into proper position for the desired orbital plane. They could determine the fuel requirements for orbital adjustments and plan missions that would last months or years. The same mathematics that Newton had formulated centuries earlier now guided the space age, transforming abstract theory into concrete engineering reality. This foundation in orbital mechanics set the stage for increasingly ambitious satellite applications. With the principles of how to keep satellites aloft thoroughly understood, attention could turn to what those satellites might accomplish during their time in orbit. With the principles of orbital mechanics understood, the next challenge facing the early space age was finding practical uses for these new artificial moons circling overhead. While the first satellites like Sputnik and Explorer carried simple instruments and radio beacons, visionaries quickly recognized that orbiting platforms could serve as relay stations in the sky, enabling communication across vast distances in ways that Earthbound transmitters never could. The first attempt to use a satellite for communication came remarkably quickly after Sputnik's launch. On December 18, 1958, just over a year after the space age began, the United States launched Project SCORE, which stood for Signal Communication by Orbiting Relay Equipment. Hidden inside an Atlas rocket that had carried it to orbit, this experimental satellite carried a tape recorder and radio equipment. The most memorable moment came when President Eisenhower's voice was broadcast from space, carrying a message of peace and goodwill to the world below. The quality was imperfect, and the satellite's batteries lasted only 13 days. But for those brief days, humanity had proven that voices could be transmitted from orbit. The next experiments took a decidedly different approach. Rather than active transmitters requiring complex electronics and power, engineers wondered if they might simply bounce radio signals off reflective surfaces in space. This led to Project Echo, a series of balloon satellites that would serve as passive reflectors for radio waves. On August 12, 1960, Echo 1 inflated in orbit to become a gleaming sphere 100 feet in diameter, bright enough to be seen from Earth with the naked eye as it caught the sunlight. Made of metallized plastic film, only a few thousandths of an inch thick, this gossamer sphere drifted through space while ground stations aimed powerful radio transmitters at its surface. Some of the radio energy bounced back to receiving stations thousands of miles away, demonstrating that transcontinental and even transoceanic communication via satellite was possible. People around the world stepped outside at dawn and dusk to watch Echo 1 pass overhead, a slow-moving artificial star crossing the heavens. The sight stirred something in the imagination, making the abstract concept of satellites tangible and visible. Here was proof that humans had placed objects in space that could be seen going about their appointed rounds, night after night. Echo 2, launched in 1964, continued these experiments with an even larger balloon, but by then, attention had shifted to more sophisticated approaches. The limitation of passive satellites was clear. They required enormous amounts of power on the ground, and only a tiny fraction of the radio energy reflected back reached the receiving stations. What was needed were active satellites that could receive signals, amplify them, and retransmit them to distant points on Earth with much greater efficiency. This required solving significant technical challenges, including developing electronic equipment that could survive the harsh environment of space, radiation exposure, extreme temperature variations, and the vacuum beyond Earth's protective atmosphere. The breakthrough came with Telstar, perhaps the most famous early communication satellite, built by Bell Telephone Laboratories and launched on July 10, 1962. Telstar was a technological marvel of its time. Roughly spherical and 34 inches in diameter, covered with solar cells to generate electricity. It contained sophisticated electronics that could receive microwave signals from ground stations, amplify them, and broadcast them back to Earth. Unlike the later geostationary satellites that would appear to hang motionless in the sky, Telstar orbited in an elliptical path, swooping from about 600 miles altitude at its lowest point to over 3,500 miles at its highest, completing each orbit in approximately 2 hours and 40 minutes. This orbit meant that Telstar was only visible to both a transmitting and receiving station on opposite sides of the Atlantic Ocean for about 20 minutes during each pass. But those 20 minutes were enough to make history. On July the 23rd, 1962, Telstar successfully relayed the first live television images across the Atlantic Ocean. Viewers in Europe saw an American flag waving at the ground station in Andover, Maine, followed by images of President Kennedy and other scenes from the United States. Americans, in turn, saw broadcasts from France and England. The pictures were grainy and the connections brief, but the impact was profound. The world suddenly felt smaller and more connected. The technical achievement represented by Telstar cannot be overstated. Its transistorized electronics had to function flawlessly in space while being bombarded by radiation and experiencing temperature swings from extreme heat to bitter cold. The satellite had to orient itself properly to aim its antenna toward Earth. Ground stations required enormous dish antennas and sophisticated tracking systems to follow the satellite's movement across the sky, maintaining their precise aim as it raced overhead at thousands of miles per hour. Split-second timing was essential, with computers calculating exactly when signals should be sent and received. Other communications satellites soon followed, each advancing the technology. Relay 1 launched in December 1962, and Syncom satellites, which achieved the first geostationary orbit in 1963, demonstrated different approaches to satellite communication. The geostationary satellites, positioned about 22,000 miles above the equator and moving at just the right speed to match Earth's rotation, offered a revolutionary advantage. They appeared to remain stationary above a fixed point on Earth's surface. This meant a ground antenna could point at the satellite continuously without needing to track its movement across the sky. The transition from experimental satellites to operational communication networks happened swiftly. In 1965, Earlybird, later renamed Intelsat-1, became the first commercial communication satellite, providing regular television and telephone service across the Atlantic. Standing in a living room in London, you could lift a telephone and speak in real time to someone in New York, your voice traveling up to a satellite and back down again in a quarter of a second, fast enough that the delay was barely perceptible. Television networks could broadcast live events from other continents, bringing distant happenings into homes with an immediacy that had never before been possible. These early communication satellites carried relatively modest capabilities by today's standards. Telstar could handle either one television channel or 600 telephone calls simultaneously. Yet this represented a quantum leap in capacity compared to the undersea cables that had previously carried a handful of telephone circuits across the oceans. Each new generation of communication satellites grew more capable, with more powerful transmitters, more sophisticated electronics, and the ability to handle more simultaneous communications. The impact rippled through society in ways both obvious and subtle. News coverage became more immediate and global. International business communication became easier and less expensive. The television images relayed by satellite helped create a shared global culture, as audiences around the world could watch the same sporting events, news broadcasts, and entertainment programming. The infrastructure of the modern connected world was beginning to take shape, though few at the time could envision just how thoroughly satellite communication would weave itself into the fabric of daily life. As these communication satellites multiplied and improved through the 1960s, they demonstrated that the orbital realm offered practical benefits beyond scientific discovery. The dreams of artificial moons had evolved into working tools that served human needs, relaying signals across distances that would have seemed impossibly far to ground-based transmitters. Meanwhile, other satellites were being developed for different purposes, each taking advantage of the unique perspective that orbit provided. As the first communication satellites began proving their worth in connecting distant points on Earth, scientists and meteorologists were looking upward with a different purpose in mind. For centuries, humans had observed clouds and wind patterns to predict tomorrow's weather, but these predictions remained frustratingly uncertain. Weather systems moved across vast distances, developing over oceans where few observers could track them. What humanity needed was a vantage point high enough to see weather patterns as they truly were. Massive, swirling systems that stretched across hundreds or thousands of miles. The dream of observing weather from above wasn't entirely new. In the 19th century, balloons had carried instruments and even photographers aloft, capturing intriguing views of cloud formations from elevated perspectives. During World War II, reconnaissance aircraft returned with photographs that, quite by accident, revealed large-scale weather patterns invisible from the ground. Meteorologists studying these images realized that if they could see the atmosphere from high enough, continuously enough, weather forecasting might transform from educated guessing into genuine science. The space age offered this possibility. If satellites could relay radio signals and eventually television broadcasts, why couldn't they photograph clouds and send those images back to Earth? The concept seemed straightforward, but translating it into reality required solving numerous technical challenges. A weather satellite would need to carry cameras that could function in the harsh environment of space, withstand temperature extremes, and transmit clear images across the vacuum to receiving stations below. In the late 1950s, as the space race accelerated following Sputnik's launch, American scientists began designing a satellite specifically for meteorological observation. They called it TIROS, an acronym for Television Infrared Observation Satellite. The project brought together expertise from NASA, the US Weather Bureau, and the military services, all recognizing the value that weather observation from space might provide. TIROS-1 took shape as an 18-sided polygon, almost drum-like in appearance, measuring just 42 inches across. Its aluminum shell protected delicate instruments from the temperature swings of orbit, where one side would bake in direct sunlight, while the other froze in shadow. 2 television cameras nestled inside this protective housing, positioned to peer down at Earth through small openings. These weren't sophisticated instruments by later standards, but rather modified versions of cameras that might be found in a television studio, adapted to survive launch forces and operate in weightlessness. On April 1st, 1960, TIROS-1 lifted off from Cape Canaveral aboard a Thor-able rocket. The date might have seemed appropriate for an April Fool's joke, but the satellite that reached orbit that day was entirely serious in purpose. Within hours of deployment, TIROS-1 began its careful spin, designed to help stabilize the spacecraft and point its cameras earthward during each orbit. The first images arrived at receiving stations with a quality that surprised even the scientists who had built the system. There, rendered in grainy black and white television pictures, were cloud patterns stretching across vast expanses of ocean and land. Meteorologists accustomed to piecing together weather maps from scattered ground observations found themselves looking at complete weather systems in a single frame. Spiral storm formations appeared as distinct, organized structures rather than abstract concepts drawn on maps. TIROS-1 operated for only 78 days before its electrical systems failed. But in that brief span, it transmitted nearly 23,000 images of Earth's atmosphere. These pictures revealed weather patterns that surface observations had never captured. Meteorologists could track storms forming over empty oceans, watch weather fronts advance across continents, and observe how cloud systems evolved hour by hour. For the first time, forecasters could see what was coming rather than merely detecting it as it arrived. The success of TIROS-1 led to a series of improved satellites. TIROS-2 followed in November of that same year, then TIROS-3, 4, and onward through a succession of increasingly capable spacecraft. Each generation carried better cameras, improved power systems, and more reliable transmitters. Engineers learned from each mission, refining techniques for keeping cameras pointed at Earth, and developing better methods for processing the vast quantities of image data flowing down from orbit. As these satellites evolved, meteorologists developed new ways to interpret what they were seeing. Cloud patterns that looked like simple white shapes in early images revealed themselves as signatures of specific weather phenomena. Tightly wound spirals indicated developing hurricanes, long. Stretched cloud bands marked the boundaries between air masses. Clear areas in otherwise cloudy regions suggested high-pressure systems. A new visual language of meteorology emerged, one that required seeing weather as it appeared from space rather than as it felt from the ground. The real breakthrough came when satellites moved from simple picture-taking to continuous observation. Early Tyros satellites had to store images on magnetic tape recorders and wait until they passed over ground stations to transmit their stored pictures. This meant delays between when a photograph was taken and when meteorologists could see it. Later, satellites gained the ability to transmit in real time as they observed, and eventually, weather satellites were placed in geostationary orbit, that special altitude where a satellite's orbital period matched Earth's rotation, allowing it to hover over the same spot continuously. From geostationary orbit, roughly 22,000 miles above the equator, weather satellites could watch entire hemispheres at once, imaging the same region every few minutes. Meteorologists gained something they had never possessed before: a constant vigil over developing weather systems. They could watch hurricanes form as small disturbances and strengthen into major storms. They could track the movement of weather systems hour by hour and see patterns that surface observations would have missed entirely. Other weather satellites flew in polar orbits, crossing from North Pole to South Pole as Earth rotated beneath them. These satellites eventually saw every part of the planet, including the polar regions where geostationary satellites couldn't look. Together, these two types of weather satellites created a comprehensive observation network that left no part of Earth's atmosphere unwatched for long. The improvement in weather forecasting accuracy that followed was measurable and significant. Predictions that had been reliable for perhaps 24 hours extended to several days. Hurricane tracking became precise enough to allow timely evacuations. Farmers could plan around approaching weather with greater confidence. Airlines could route flights to avoid storms they could now see developing far in advance. But perhaps most importantly, weather satellites revealed Earth's atmosphere as a connected, dynamic system. Storms forming over the Pacific Ocean influenced weather patterns that would eventually reach other continents. Seasonal shifts appeared as planetary-scale rearrangements of air and moisture. The atmosphere revealed itself not as a collection of local weather events, but as a single, integrated system wrapping the entire globe. As this chapter of the satellite story drew toward its close, weather observation from space had become so fundamental to meteorology that forecasting without it seemed almost unimaginable. The technology that began with grainy television images from Tyros 1 had matured into sophisticated systems monitoring temperature, humidity, wind patterns, and atmospheric composition. Yet the basic principle remained the same as that first insight. To understand weather, one must see it whole, from above, as satellites had made possible. As weather satellites began revealing patterns in the clouds above, another urgent need was becoming clear to military planners and commercial shipping operators alike. Navigating across vast oceans had always required skilled observation of stars, careful, dead reckoning, and a measure of uncertainty that sometimes proved costly. Ships could find themselves hundreds of miles off course without knowing their precise position. The same satellites that were orbiting overhead, transmitting data about storms and cloud cover, suggested an intriguing possibility. Perhaps these artificial moons circling Earth could also tell travelers exactly where they were. The United States Navy faced this challenge most acutely. Submarines carrying nuclear missiles needed to know their exact positions before launching. Yet spending weeks underwater made traditional celestial navigation impossible. Surface ships crossing empty ocean expanses would benefit enormously from reliable positioning that didn't depend on seeing the stars. The problem was fundamentally one of geometry and timing, and satellites offered a solution. In the late 1950s, researchers at the Applied Physics Laboratory of Johns Hopkins University began developing what would become the transit system. The concept emerged partly from observing Sputnik itself. Scientists tracking the Soviet satellite's radio signals noticed something interesting. As Sputnik passed overhead, the frequency of its transmitted signal appeared to shift due to the Doppler effect, the same phenomenon that makes a train whistle sound higher pitched as it approaches and lower as it recedes. By carefully measuring this frequency shift, observers on the ground could determine aspects of the satellite's orbit. The researchers realized this principle could work in reverse. If a satellite's precise orbit was known, measuring the Doppler shift of its signals could reveal the observer's position on Earth. The transit satellites that emerged from this insight were elegant in their simplicity. Each satellite would broadcast radio signals containing information about its exact orbital position and the current time. A receiver on a ship would detect these signals and measure how the frequency changed as the satellite moved across the sky. From this measurement, combined with knowledge of the satellite's orbit, computers could calculate the ship's latitude and longitude. The accuracy depended on receiving a complete pass of the satellite overhead, which took about 15 minutes. The first experimental transit satellite, Transit 1A, launched in September 1959, but failed to reach orbit when the rocket malfunctioned. Transit 1B succeeded 3 months later, in April 1960, becoming the first satellite specifically designed for navigation. The system proved the concept worked. Ships equipped with receivers and small computers could indeed determine their positions by listening to satellites. Over the next few years, additional transit satellites joined the constellation. The Navy needed multiple satellites because each one could only provide a position fix when it passed overhead. With satellites in polar orbits, crossing over the North and South Poles, a ship at mid-latitudes might wait an hour or more between fixes. More satellites meant shorter waiting times. By 1964, the transit system became operational for the Navy's Polaris submarine fleet, giving these vessels the precision navigation they required. The satellites themselves were modest compared to later navigation systems. Transit satellites weighed around 170 pounds and operated in orbits roughly 700 miles above Earth. They were shaped like cylinders about 2 feet in diameter, covered with solar panels that generated electrical power. Inside, radio transmitters broadcast on 2 frequencies, allowing receivers to compensate for signal delays caused by Earth's ionosphere, the layer of charged particles in the upper atmosphere that affects radio waves. Maintaining accurate time proved essential to the system. Each transit satellite carried a crystal-controlled oscillator that kept time precisely, so the orbital position information it transmitted would be synchronized properly. The satellites also carried small radiation detectors, continuing the tradition of combining practical purposes with scientific observation that characterized early satellite development. Ground stations tracked the transit satellites constantly, measuring their exact orbits and uploading updated orbital information to the satellites several times each day. These measurements had to be extremely precise because any error in knowing the satellite's true position would translate directly into navigation errors for ships using the system. The tracking stations used the Doppler measurements from the satellites themselves, closing an elegant loop where the navigation signals also enabled precise orbit determination. Using transit required patience. A ship's navigator would wait for a satellite pass, then carefully record the Doppler shift measurements over approximately 15 minutes. The ship had to maintain steady course and speed during the measurement, or account for any maneuvers in the calculations. After the satellite passed, a small computer would process the data, typically taking several minutes to calculate the position fix. The result was accuracy within about 200 meters, a remarkable improvement over previous methods for ships out of sight of land. The transit system served the Navy reliably for decades and eventually became available for civilian use as well. Commercial shipping companies, fishing vessels, and survey ships adopted the technology. Receivers became smaller and more affordable through the 1970s and 80s. The system demonstrated conclusively that satellites could provide global navigation services, though the limitations became increasingly apparent. Users wanted more frequent fixes, continuous positioning instead of periodic updates, and better accuracy. These demands would eventually drive development of more sophisticated satellite navigation systems. What transit accomplished, beyond its immediate practical value, was establishing fundamental principles that would guide all future satellite navigation. The system proved that precisely controlled orbits and accurate timing could transform radio signals into position information. It demonstrated that a constellation of satellites could provide global coverage, though more satellites were needed for continuous service. The challenges of accounting for atmospheric effects, maintaining satellite clocks, and computing positions from radio measurements all received practical solutions that would inform later designs. The engineers and scientists who developed transit created more than a navigation tool for submarines. They opened a pathway that would eventually lead to positioning technology in millions of cars, phones, and countless other devices. Navigation from the sky had become reality, adding another dimension to humanity's growing network of artificial satellites. As these transit satellites hummed quietly in their polar orbits, broadcasting their patient signals to the oceans below, they carried forward the same pioneering spirit that had lifted Sputnik skyward just a few years earlier. The age of satellite navigation had begun, still in its early steps, but moving steadily towards something far more comprehensive. As the navigation satellites traced their methodical paths across the heavens, providing guidance to ships and aircraft below, another application for orbital observation was quietly taking shape. The same vantage point that allowed satellites to receive signals and track position could also be used to look downward, studying Earth itself in ways previously unimaginable. While weather satellites had demonstrated the value of watching cloud patterns from space, scientists and resource managers began to wonder what else might be learned from systematic observation of the planet's surface. In the late 1960s, the idea emerged to create a satellite specifically designed to survey Earth's land areas. The concept was straightforward yet ambitious. A spacecraft would orbit the planet in a regular pattern, photographing the surface below in multiple wavelengths of light, creating a continuous record of how the landscape appeared and changed over time. This systematic approach to Earth observation would be different from earlier satellites that captured occasional images. Instead, it would return to the same locations repeatedly, building a comprehensive archive of the planet's features. The satellite that would make this vision real took shape at NASA's Goddard Space Flight Center. Originally called the Earth Resources Technology Satellite, it would later be renamed Landsat, a fitting description of its purpose. The spacecraft carried two innovative imaging systems that worked in complementary ways to capture information about the surface below. A return beam Vidicon camera system recorded images much like a television camera, while a multispectral scanner measured reflected light in different wavelengths, including some beyond what human eyes could detect. On July 23, 1972, Landsat 1 lifted off from Vandenberg Air Force Base in California, beginning a program that would continue for decades to come. The satellite entered a sun-synchronous polar orbit, passing over the North and South poles, while Earth rotated beneath it. This orbital path meant that the satellite crossed the equator at the same local time each day, ensuring consistent lighting conditions for its observations. As Earth turned through a complete rotation, Landsat's orbit shifted slightly westward, allowing its instruments to observe a different strip of the planet's surface on each pass. From its altitude of nearly 570 miles above Earth, Landsat 1 could observe a swath of territory about 115 miles wide with each orbit. The satellite circled the planet 14 times per day, and every 18 days its ground track repeated, meaning it photographed the same locations on a regular schedule. This systematic coverage transformed Earth observation from occasional snapshots into continuous monitoring. The images that flowed back to receiving stations revealed landscapes in extraordinary detail. Scientists could distinguish features as small as about 160 feet across, though different versions of the sensors had varying resolutions. More importantly, the multispectral scanner recorded information in 4 different wavelengths, including infrared light, invisible to human eyes. Plants reflect infrared light strongly, while absorbing visible light for photosynthesis. So vegetation appeared bright in infrared images, even when it looked dark green to the eye. This allowed researchers to assess plant health and distinguish between different types of vegetation. Agricultural scientists quickly recognized the value of this orbital perspective. By analyzing how fields reflected different wavelengths of light, they could estimate crop health and predict yields across vast regions. Instead of surveying farms individually, a single satellite image could reveal the condition of thousands of square miles of farmland simultaneously. Government agencies began using Landsat data to forecast wheat and corn production, improving agricultural planning. Foresters found similar value in monitoring woodland areas. The satellite could identify different forest types, track where logging had occurred, and reveal damage from fires, disease, or insect infestations across remote wilderness areas that would be difficult to survey from the ground. The regular 18-day revisit cycle meant that changes could be detected relatively quickly, alerting managers to problems requiring attention. Water resource managers discovered they could track reservoirs, rivers, and seasonal changes in wetlands. The satellite sensors distinguished water from surrounding land clearly, and repeated observations showed how water levels fluctuated with seasons and years. In arid regions where water resources were precious, this orbital monitoring provided crucial information for planning and management. Geologists found themselves with a powerful new tool for understanding Earth's structure. Landsat images revealed fault lines, rock formations, and mineral deposits that were difficult to recognize from ground level. The orbital perspective allowed scientists to see patterns spanning hundreds of miles, revealing relationships between geological features that had previously gone unnoticed. Mining companies began using satellite data to identify promising areas for exploration. Urban planners used Landsat images to track city growth and development patterns. The satellite could clearly distinguish between built-up areas, agricultural land, and natural vegetation, allowing researchers to document how cities expanded over time. This information helped communities plan infrastructure and understand the environmental impacts of development. Environmental scientists discovered that Landsat provided a unique record of planetary change. Because the satellite returned to the same locations every 18 days and used consistent methods to record observations, scientists could compare images from different years to detect changes in land cover. Forests cleared for agriculture appeared dramatically different in the satellite's multispectral images. Wetlands converted to development showed clear signatures. Desert areas affected by changing climate revealed their transformation. The satellite operated far longer than its intended one-year mission. Landsat 1 continued sending back images until January 1978, having observed Earth for more than 5 years. Its success led to the launch of Landsat 2 in 1975, ensuring continuity of observations. Additional satellites followed, each incorporating improved sensors and capabilities, while maintaining consistency with earlier data. Perhaps the most profound impact of Landsat came from the simple fact of continuous observation. Before this orbital monitoring began, understanding large-scale environmental changes required piecing together scattered observations and aerial photographs taken at different times under varying conditions. Landsat provided systematic, consistent data that accumulated into an invaluable archive. Scientists studying deforestation in the Amazon, agricultural expansion in Africa, or glacier retreat in mountain ranges all drew on this growing collection of orbital observations. The data also proved remarkably versatile. The same images that helped farmers assess crops could assist disaster response teams mapping flood extent or fire damage. Archaeologists found they could sometimes identify buried ancient structures by subtle differences in vegetation patterns that appeared in multispectral imagery. Coastal managers tracked erosion and sediment movement in estuaries and river deltas. As Landsat continued its patient observation of Earth's surface, the program demonstrated that satellites could do more than communicate messages or provide navigation. They could serve as tireless observers, documenting the planet's features and changes with a consistency and scope impossible to achieve from the ground. The technology that had begun with simple beeping radio transmitters had evolved into sophisticated instruments for understanding our world, watching over forests and fields, rivers and cities, mountains and plains, building a portrait of Earth as it changed through seasons and years, one orbital pass at a time. The journey from observing Earth's resources to pinpointing exact locations anywhere on the planet represents one of satellite technology's most remarkable transformations. While Landsat had been systematically photographing the ground below, another constellation of satellites was quietly being assembled overhead, one that would eventually change how billions of people navigate their daily lives. The Global Positioning System began not as a tool for finding restaurants or planning road trips, but as a solution to a distinctly military challenge. Throughout the 1960s and 70s, the United States Department of Defense grappled with a fundamental question: how could ships, aircraft, and ground forces determine their precise positions anywhere on Earth, in any weather, at any time of day or night? Previous navigation methods relied on visible landmarks, celestial observations when skies were clear, or radio beacons with limited range. What was needed was something universal, something that could work equally well over featureless ocean, trackless desert, or dense jungle canopy. The concept that emerged drew upon lessons learned from earlier satellite navigation systems like transit, which had successfully guided submarines across the oceans. But transit had limitations. Ships had to wait for a satellite to pass overhead, and the system worked poorly for fast-moving aircraft. The new system would require many more satellites, arranged so that several would always be visible from any point on Earth's surface. It would also need extraordinarily precise timekeeping and complex calculations performed in fractions of seconds. In the early 1970s, the various branches of the American military were developing separate navigation satellite programs. The Air Force had one approach, the Navy another. Recognizing the inefficiency of parallel efforts, military planners consolidated these programs into a single unified system. By 1973, the program that would become GPS was officially established. The system's name itself was straightforward and descriptive. It would provide positioning on a global scale. The fundamental principle underlying GPS is beautifully simple, though its implementation required solving tremendously complex technical challenges. Imagine standing in a park and knowing you are exactly 100 meters from a particular tree. This tells you something about your location, but not precisely where you stand. You could be anywhere on a circle of that radius around the tree. Now, suppose you also know you are exactly 75 meters from a second tree. Your possible locations narrow to just 2 points where those circles intersect. Add a third tree at a known distance, and suddenly, only one position satisfies all three measurements. This is trilateration, and GPS applies this ancient surveying technique across 3 dimensions, with satellites serving as reference points, positioned with exquisite precision in space. Each GPS satellite carries atomic clocks, timepieces so accurate they would neither gain nor lose a second in tens of thousands of years. These clocks continuously broadcast the precise time and the satellite's exact position. A receiver on the ground, whether in a ship, aircraft, or handheld device, listens to these signals from multiple satellites simultaneously. By measuring how long each signal took to arrive, and knowing that radio waves travel at the speed of light, the receiver calculates its distance from each satellite. With information from at least 4 satellites, it determines latitude, longitude, altitude, and even the precise time. The first experimental GPS satellite lifted off in 1978. engineers designated these early spacecraft Block 1 satellites, prototype versions that would test whether the ambitious system could actually work. Over the following 7 years, 10 more Block 1 satellites joined the first in orbit, arranged in carefully calculated paths that would eventually form a global network. Each satellite orbited approximately 12,000 miles above Earth, completing 2 circuits around the planet each day. From the beginning, accuracy required accounting for effects that seemed to belong more to theoretical physics than practical engineering. Einstein's theories of relativity predicted that time would flow differently for clocks moving at high speeds and experiencing different gravitational strength than clocks on Earth's surface. These effects were tiny, measured in microseconds, but even microsecond errors in timing would translate to positioning errors of hundreds of feet. GPS designers built corrections for relativistic effects directly into the system, providing one of the most commonplace daily confirmations of Einstein's revolutionary insights. The full constellation of operational satellites, designated Block 2, began launching in 1989. These satellites were larger, more capable, and designed for longer operational lives than their experimental predecessors. They carried more powerful transmitters, improved atomic clocks, and better protection against the harsh radiation environment of space. 28 Block 2 satellites reached orbit over the following several years, creating the complete GPS constellation. For the first decade of GPS operation, the system's full accuracy remained restricted to authorized military users. Civilian receivers could access GPS signals, but those signals were intentionally degraded through a process called selective availability, which introduced random errors, limiting civilian accuracy to about 100 meters. Military receivers with special equipment could decode additional signal information that provided positioning accurate to within 15 meters or better. The value of GPS became dramatically apparent during military operations in the early 1990s, when coalition forces operating in desert environments relied heavily on satellite navigation. Soldiers, pilots, and sailors could determine their positions precisely in landscapes where traditional navigation proved challenging. The technology that had taken nearly 2 decades to develop showed its worth in conditions where certainty about location could mean the difference between success and failure. Yet even as GPS demonstrated its military utility, its potential for civilian applications became increasingly evident. Commercial aviation saw opportunities for improved navigation and landing systems. Shipping companies recognized benefits for tracking vessels and optimizing routes. Surveyors and map makers began using GPS to establish reference points with unprecedented accuracy. In face of 2000, the deliberate degradation of civilian signals was discontinued, instantly improving accuracy for civilian users by a factor of 10. This decision opened floodgates of innovation. Portable GPS receivers became smaller and less expensive. Automobile navigation systems appeared, displaying moving maps that showed drivers their exact positions. Hikers carried handheld units into wilderness areas. Scientists used GPS to track animal migrations, measure continental drift, and monitor glacial movement. The satellites that had been designed to guide missiles and troops instead guided delivery trucks, helped farmers plant crops efficiently, and enabled countless people to find their way in unfamiliar places. The GPS constellation itself required continuous maintenance and upgrading. Satellites aged, their solar panels degraded, and their atomic clocks occasionally drifted despite their extraordinary precision. New satellites launched regularly to replace aging ones and to introduce improved capabilities. Later generations carried additional signals for enhanced accuracy and reliability. Ground stations scattered around the world monitored the satellites continuously, updating their orbital information and ensuring signal quality. As we drift towards sleep, we might consider that somewhere above, at this very moment, approximately 30 satellites are circling Earth, each broadcasting its precise position and time. They form an invisible infrastructure that has become as essential to modern life as electrical grids or telephone networks. From that experimental satellite launched decades ago to the sophisticated constellation operating today, GPS transformed abstract mathematical calculations into a tool so commonplace we scarcely notice its presence, guiding us through our days with quiet, orbital precision. While the global positioning system was transforming everyday life on Earth's surface, another category of satellites was quietly advancing human understanding of the universe itself. These scientific satellites carried instruments designed not to serve commerce or navigation, but to answer fundamental questions about the environment surrounding our planet and the forces that shape our place in space. The realm beyond Earth's protective atmosphere holds mysteries that cannot be fully studied from the ground. Our thick blanket of air, while essential for life, blocks or distorts many forms of radiation and particles streaming through space. To truly understand the invisible forces surrounding our world, instruments needed to rise above this atmospheric veil. Scientific satellites became humanity's sensing organs in this alien environment, extending our perception into regions where human bodies could not venture for long. The earliest scientific satellites revealed that space near Earth was far from empty. Rather than the void that many had imagined, the region surrounding our planet teemed with invisible activity. Charged particles trapped by Earth's magnetic field spiraled along invisible lines of force. Streams of particles from the sun washed past the planet in a constant solar wind. Cosmic rays from beyond our solar system peppered through space at nearly the speed of light. Each discovery raised new questions, prompting missions to measure, map, and understand these phenomena. Satellites studying the upper atmosphere revealed its unexpected complexity. The thin air at orbital altitudes behaves nothing like the weather-driven atmosphere below. Here, ultraviolet radiation from the sun breaks molecules apart into component atoms. Free electrons and ions create electrically charged layers that reflect radio waves, making long-distance communication possible. The atmosphere at these heights expands and contracts dramatically as solar activity varies, sometimes creating enough drag to alter satellite orbits. Understanding this environment required patient observation over months and years, recording how conditions changed with the seasons, the solar cycle, and sudden storms from the sun. The solar wind itself became a subject of intense study. This continuous outflow of charged particles from the sun's outer atmosphere streams past Earth at hundreds of miles per second, carrying with it the sun's magnetic field. When this solar wind encounters Earth's own magnetic field, complex interactions occur. Sometimes the two magnetic fields reconnect, allowing solar particles to cascade into Earth's upper atmosphere near the poles, creating the shimmering curtains of aurora that dance across Arctic and Antarctic skies. Scientific satellites positioned between the Sun and Earth became sentries, providing advance warning of particularly intense solar storms that could disrupt communications and power grids. Earth's magnetosphere, that vast region of space dominated by our planet's magnetic field, emerged as a dynamic and structured domain through satellite observations. Rather than a simple bubble, the magnetosphere has a teardrop shape, compressed on the side facing the sun and stretched into a long tail on the night side, extending past the moon's orbit. Within this magnetic cocoon, different regions harbor different populations of trapped particles. Satellites crossing these boundaries recorded abrupt changes in their environment, mapping an invisible architecture in space. Cosmic rays, those high-energy particles originating from supernovae and other violent events across the galaxy, provided another avenue of scientific inquiry. Unlike particles from the sun, cosmic rays carry enormous energies, some arriving with more punch than a well-thrown baseball compressed into a single atomic nucleus. Understanding where these particles come from, how they achieve such tremendous speeds, and what they can tell us about distant cosmic events required satellites with specialized detectors. These missions recorded not just the number of arriving particles, but their energies, their directions, and their composition, slowly building a picture of violent processes occurring light years away. Some scientific satellites turn their instruments toward Earth itself, not to photograph its surface, but to study global patterns in ways impossible from the ground. Satellites measuring Earth's gravitational field with extreme precision revealed that our planet's gravity varies slightly from place to place, reflecting the distribution of mass beneath the surface. These tiny variations help scientists understand movements of water, melting of ice sheets, and even the slow churning of rock in Earth's mantle. Other satellites measured subtle changes in Earth's magnetic field, which is generated deep in the planet's liquid iron core and slowly shifts over time. The ozone layer, that tenuous concentration of three-atom oxygen molecules in the stratosphere that shields the surface from harmful ultraviolet radiation, became a subject of satellite monitoring in the 1970s and 80s. Instruments designed to measure the thickness and distribution of this protective layer began revealing seasonal variations and, eventually, alarming thinning over Antarctica each spring. These satellite observations provided clear evidence of human impact on the global atmosphere, data that could not have been gathered by any other means. The continuous monitoring possible only from space allowed scientists to track how the ozone layer responded to international agreements reducing harmful chemicals. Temperature measurements from space offered another global perspective. While weather stations on the ground provide detailed local information, satellites equipped with sensitive radiometers could measure the temperature of the atmosphere at different altitudes across the entire planet, day and night, over oceans and remote regions where no weather stations exist. These measurements, accumulated over decades, contribute to understanding how Earth's climate system functions and how it changes over time. Scientific satellites studying Earth's radiation budget measured both the incoming energy from the sun and the outgoing infrared radiation Earth emits back into space. The balance between these two determines whether the planet warms or cools. Small satellites carrying precision instruments tracked these energy flows, providing data essential for understanding the complex systems that regulate Earth's temperature. The versatility of satellites as scientific platforms meant that researchers could study phenomena on many different scales simultaneously. A single satellite might carry instruments measuring local conditions right around the spacecraft, while other instruments observed global patterns. Some satellites flew in coordinated formations, making simultaneous measurements at different locations to understand how disturbances propagate through space. Others maintained orbits that kept them in continuous sunlight, providing uninterrupted power for long-term observations. These scientific missions typically received less public attention than dramatic weather images or navigation services that people used directly. Yet they steadily accumulated knowledge about our planet's environment and its context in space. Each careful measurement, each patient observation, each unexpected discovery contributed to a growing understanding of Earth, not as an isolated sphere, but as an active participant in the larger space environment, constantly interacting with the Sun and responding to forces beyond human perception. As these scientific satellites continued their quiet work of observation and measurement, other missions prepared to turn their instruments away from Earth entirely, looking outward to the universe beyond, ready to reveal cosmic wonders with unprecedented clarity. While satellites had already taught humanity so much about Earth's atmosphere, magnetic fields, and weather patterns, scientists dreamed of looking outward with equal clarity. The stars and galaxies that had captivated human imagination since the first person gazed upward remained veiled by Earth's restless atmosphere. Even the most powerful ground-based telescopes saw the universe through hundreds of miles of shifting air, water vapor, and dust that blurred and dimmed celestial light. The solution, astronomers realized, would be to place a telescope above it all, in the perfect darkness of space itself. The concept of a space telescope emerged in the 1940s when astronomer Lyman Spitzer wrote a paper describing the advantages of astronomical observations from beyond Earth's atmosphere. The atmosphere not only caused stars to twinkle, a poetic phenomenon that frustrated scientists seeking clear images, but also blocked entire wavelengths of light from reaching ground-based instruments. Ultraviolet radiation, crucial for understanding hot young stars and energetic cosmic phenomena, never made it through the atmospheric shield that protected life on Earth's surface. A telescope in orbit would see the universe with unprecedented clarity across a broader spectrum of light. For decades, this remained a beautiful idea, waiting for technology to catch up. Building a telescope was one thing. Building one that could survive the violence of a rocket launch, function in the vacuum of space, and remain stable enough to capture sharp images across millions of miles was quite another. Through the 1960s and 1970s, as satellite technology matured, NASA and astronomers refined plans for what would become the Hubble Space Telescope, named after Edwin Hubble, the astronomer who had discovered that the universe was expanding. The telescope took shape through the 1980s as a collaborative effort involving thousands of engineers, scientists, and technicians. Unlike satellites that pointed toward Earth, this one would face outward, away from our planet. Its primary mirror measured 2.4 meters in diameter, smaller than many ground-based telescopes, but sufficient for extraordinary discoveries when freed from atmospheric interference. The mirror's surface had to be polished to perfection, smoother than any mirror ever made, accurate to within a fraction of a wavelength of light. Engineers designed the entire observatory to be about the size of a large school bus, weighing over 24,000 pounds when fully assembled. The instruments inside would capture images across visible light, ultraviolet, and infrared wavelengths. Solar panels would unfold like wings to power the systems. Gyroscopes and reaction wheels would allow the telescope to point with exquisite precision, holding steady on distant targets while traveling through space at thousands of miles per hour. Perhaps most remarkably, NASA designed Hubble to be serviceable. Astronauts could visit it aboard the space shuttle to replace instruments, upgrade technology, and perform repairs that would extend its operational life far beyond what any previous satellite had achieved. On April the 24th, 1990, Space Shuttle Discovery lifted off from Kennedy Space Center, carrying Hubble in its cargo bay. The next day, the crew deployed the telescope into orbit approximately 340 miles above Earth's surface. The observatory unfurled its solar arrays, activated its systems, and began the process of opening its eye on the universe. Scientists and astronomers worldwide anticipated the first images with extraordinary excitement. When those first images arrived, however, they brought disappointment along with wonder. The pictures were sharper than ground-based telescopes could achieve, yet they weren't as crisp as expected. Something was wrong. After careful analysis, engineers discovered that Hubble's primary mirror had been ground to the wrong specification, a mistake of less than 1/50th the thickness of a human hair, but enough to cause spherical aberration that blurred the images. The most expensive and sophisticated telescope ever built had launched with flawed vision. Rather than accepting this limitation, NASA planned an audacious repair mission. In December 1993, Space Shuttle Endeavour carried a crew of astronauts on a service call to Hubble. Over 5 spacewalks spanning 11 days, astronauts installed corrective optics that compensated for the mirror's flaw, essentially giving Hubble a pair of glasses. They also replaced solar panels and other components. The mission required extraordinary precision, working with tools while wearing pressurized gloves, making repairs on a satellite moving at over 17,000 miles per hour. When Hubble's corrected images began arriving in early 1994, they exceeded even optimistic expectations. The universe revealed itself in stunning detail and color. The telescope captured images of stellar nurseries where new stars formed inside vast clouds of gas and dust. The pillars of creation in the Eagle Nebula rising like cosmic mountains. It photographed the final moments of dying stars, their outer layers blown into space in delicate shells and rings of glowing gas. Galaxies billions of light years away appeared in images showing hundreds of galaxies within a single frame, each one containing hundreds of billions of stars. Hubble transformed astronomy from a field that sometimes struggled to capture public imagination into one that regularly produced images of such beauty. They appeared in art galleries and on walls far from any laboratory. The telescope discovered that supermassive black holes lurked at the centers of most galaxies. It measured the expansion rate of the universe with new precision, helping determine the cosmos was approximately 13.8 billion years old. It captured images of distant planets in our own solar system, tracked storms on Jupiter, and even detected atmospheres around planets orbiting other stars. Astronauts returned to Hubble several more times, each servicing mission, upgrading instruments, and replacing aging components. These visits extended the telescope's capabilities and operational life far beyond its original design. Each new generation of instruments brought enhanced sensitivity and new wavelength coverage, ensuring Hubble continued making groundbreaking discoveries decades after its launch. The telescope's orbit carried it around Earth every 97 minutes, but its gaze remained fixed on objects so distant their light had traveled for billions of years before reaching Hubble's mirror. In quiet darkness, free from the interference of atmosphere or daylight, the observatory accumulated photons from the edge of the observable universe. Some images required days of continuous exposure, the telescope returning again and again to point at the same patch of apparently empty sky, gathering faint light until distant galaxies emerged from darkness. Hubble operated as a satellite unlike any before it, not watching Earth, but expanding human perspective by revealing the universe's vastness and beauty. It showed us galaxies colliding in slow-motion cosmic dances spanning millions of years. It captured the birth and death of stars, the building blocks of future solar systems. It demonstrated that the universe contained far more galaxies than previously imagined, each one an island of billions of stars, many likely accompanied by their own planets. As the observatory continued its endless orbit, circling Earth while peering into the depths of space and time, it represented both triumph over technical challenges and the power of human curiosity. The satellite that nearly failed at birth became one of the most productive scientific instruments ever created, its images simultaneously advancing knowledge and inspiring wonder across generations. As the Hubble Space Telescope continued its solitary vigil high above Earth's atmosphere, a different kind of orbital architecture was taking shape across the heavens. While Hubble represented the power of a single, exquisitely crafted instrument, the future of satellite technology increasingly belonged to something more ambitious. Networks of satellites working together as coordinated systems, their individual capabilities multiplied through collaboration. The concept of satellite constellations emerged from a simple observation. A single satellite, no matter how sophisticated, could only observe or communicate with a limited portion of Earth's surface at any given moment. As it traced its orbital path, entire continents would pass beyond its reach for hours at a time. For truly continuous global coverage, whether for communications, navigation, or observation, multiple satellites needed to work in concert, their orbits carefully choreographed to ensure that at least one member of the constellation remained visible from any point on the planet at all times. The earliest satellite networks developed organically as operators launched successive spacecraft to replace aging predecessors or expand coverage. The Syncom and early bird communication satellites of the 1960s gradually multiplied into clusters positioned at different longitudes in geostationary orbit. Each satellite remained fixed above a particular region, and together they formed an arc of relay stations spanning much of the globe. Engineers discovered that by spacing these satellites approximately 20,300 miles above the equator at regular intervals, they could create nearly complete coverage of Earth's populated regions, with signals passing from ground station to satellite and back to ground, carrying telephone conversations and television broadcasts across oceans in the blink of an eye. The International Telecommunications Satellite Organization, or Intelsat, pioneered this approach. Beginning with a single satellite named Early Bird in 1965, the system grew to encompass dozens of spacecraft positioned around the equatorial arc. Each new generation brought increased capacity, able to handle more telephone circuits and television channels simultaneously. The satellites themselves became larger and more complex, their solar panels stretching wider to generate the power needed for stronger transmitters, their antennas growing more sophisticated to focus signals on specific regions below. Managing these networks presented challenges that single satellite operators had never encountered. Orbital positions needed careful allocation to prevent interference between satellites serving similar regions. Ground controllers developed procedures to track multiple spacecraft simultaneously, monitoring the health and status of each, while coordinating handoffs as communications passed from one satellite's coverage area to another. The complexity grew with each addition to the constellation, requiring increasingly sophisticated ground systems and operational protocols. The global positioning system, as we learned, took the constellation concept to new heights of precision. Rather than a handful of satellites in geostationary orbit, GPS required 24 spacecraft arranged in 6 different orbital planes, each inclined 55 degrees to the equator. This configuration ensured that at least 4 satellites remained visible from any point on Earth at any time, providing the geometric diversity needed for accurate position calculations. The system operated like a precisely synchronized cosmic dance, each satellite broadcasting timing signals referenced to atomic clocks. The entire constellation maintained in careful formation through continuous monitoring and occasional orbital adjustment. Other nations and regional organizations developed their own navigation constellations, recognizing the strategic importance of independent positioning capabilities. Russia's GLONASS system deployed its own network of satellites in orbital planes similar to GPS. Europe's Galileo constellation added another layer to the global navigation infrastructure, as did China's Beidou system. These networks shared the orbital environment, their signals coexisting in space, allowing receivers on the ground to potentially use satellites from multiple constellations simultaneously for even greater accuracy. Communication satellite constellations evolved in different directions depending on their intended purpose. The Iridium system, conceived in the 1980s and deployed in the 1990s, took a revolutionary approach to mobile telephone coverage. Rather than positioning satellites in geostationary orbit where they remained fixed above specific locations, Iridium placed 66 satellites in low Earth orbit, sweeping across the sky at approximately 485 miles altitude. This network created a mesh of orbital pathways, each satellite able to communicate not only with ground stations and user terminals below, but also with adjacent satellites through crosslinks. A phone call placed from one remote location could hop from satellite to satellite across the constellation before descending to reach its destination, enabling truly global mobile communications, including coverage over oceans and polar regions where no ground infrastructure existed. The technical complexity of maintaining such a system proved formidable. Each Iridium satellite circled Earth roughly every 100 minutes, meaning the network's configuration continuously changed from the perspective of any ground location. Controllers needed to track all 66 spacecraft simultaneously, ensuring they maintained proper spacing and orientation, their crosslinks connecting to the correct neighbors as orbital paths crossed and separated. The system required careful planning to accommodate the addition of new satellites or the controlled deorbit of those reaching end of life, all while maintaining seamless service. Earth observation constellations brought their own design considerations. Weather satellites positioned in geostationary orbit provided continuous monitoring of specific regions, their instruments returning images every few minutes. But satellites in polar orbits offer different advantages, passing over the entire planet as Earth rotated beneath them, capturing high-resolution imagery of every location. The most effective weather monitoring systems combined both approaches, using geostationary satellites for rapid updates of developing weather patterns, while polar orbiters provided detailed global coverage twice daily. Commercial Earth. Imaging companies deployed constellations of small satellites in low orbit to increase observation frequency. While a single satellite might revisit the same location only once every few days, a coordinated network could image any point on Earth multiple times daily, monitoring construction projects, agricultural development, disaster response, or environmental changes with unprecedented temporal resolution. These constellations grew to include dozens of satellites, their combined data streams creating continuous records of human activity and natural processes across the planet's surface. The coordination required to operate these networks extended beyond individual satellite controllers to international cooperation frameworks. The International Telecommunication Union allocated orbital slots and radio frequencies to prevent conflicts between systems operated by different nations and organizations. As the orbital environment grew more crowded, particularly the valuable geostationary arc where satellites needed precise positioning, these coordination efforts became increasingly critical. Operators shared information about satellite positions and planned maneuvers, working to ensure that their expanding constellations could coexist in the finite space above Earth. Satellite networks also created redundancy and resilience. A single satellite's failure might once have interrupted critical services. But within a constellation, remaining spacecraft could often compensate for a lost member, redistributing coverage until replacement satellites could be launched. This robustness made networks attractive for applications requiring high reliability, from military communications to civil aviation navigation aids, to environmental monitoring systems that needed continuous operation year after year. As these constellations matured and proliferated, the night sky itself began to change in subtle ways. Observers with sharp eyes could sometimes spot satellites passing overhead, sunlight glinting from solar panels during evening twilight or pre-dawn darkness. These moving lights represented humanity's growing presence in orbit, networks of machines working ceaselessly above, connecting continents, guiding travelers, watching weather patterns, and extending our reach beyond the atmosphere that cradled civilization below. As the networks of satellites grew more sophisticated and interconnected, a remarkable transformation began to unfold in the nature of space operations themselves. What had started as the exclusive domain of government agencies and national space programs gradually opened to a new kind of participant. Private enterprise, with its entrepreneurial spirit and commercial ambitions, began to see the vast potential waiting in the darkness above our atmosphere. The foundations for commercial satellite operations had been quietly forming since the earliest days of spaceflight. Even as government agencies launched their pioneering missions, forward-thinking individuals recognized that satellites could deliver services people and businesses would pay for. The challenge lay in transforming what had been purely scientific and military endeavors into viable commercial ventures that could sustain themselves through market forces rather than government budgets. The Communications Satellite Corporation, known as ComSat, emerged in 1963 as one of the first entities designed to bridge the gap between government capability and commercial operation. Created through an act of the United States Congress, yet structured as a private corporation, ComSat represented a new hybrid model for space activities. The organization took the proven technology of communication satellites and began developing it into a service that could connect people across oceans and continents for telephone calls, television broadcasts, and eventually data transmission. Just 2 years later, the International Telecommunications Satellite Organization, or Intelsat, expanded this concept to the global stage. With multiple nations participating, Intelsat created a cooperative framework for providing satellite communication services worldwide. The organization launched a series of satellites, each generation more capable than the last, creating an orbital infrastructure that businesses and governments could access for their communication needs. By the 1970s, Intelsat satellites were carrying the majority of international telephone traffic, along with television broadcasts that brought distant events into living rooms around the world. The economics of satellite operations presented fascinating challenges. Launching a satellite required enormous upfront investment, with rockets costing millions of dollars, and the satellites themselves representing years of engineering and manufacturing work. Yet once successfully positioned in orbit, a communication satellite could operate for years, potentially decades, generating steady revenue with relatively modest operating costs. The key to profitability lay in maximizing the use of each satellite's capacity, selling transponder space and bandwidth to multiple customers who could share the orbital platform's capabilities. Television broadcasters became major customers for satellite services, discovering that satellites offered far more efficient distribution than terrestrial networks. Rather than sending programs over land through chains of relay stations, broadcasters could uplink their signal to a satellite once, and the satellite would beam it down across entire continents. Cable television systems, which proliferated during the 1980s, relied heavily on satellites to receive programming at their local distribution centers. Individual channels rented satellite capacity to reach cable systems nationwide, creating an entirely new media landscape. The market for private satellite communications expanded dramatically as technology advanced. Companies began operating their own dedicated satellites, rather than renting space on shared platforms. Hughes Aircraft Company became a major manufacturer of commercial satellites, producing spacecraft that served customers around the globe. Other manufacturers joined the market, creating competition that drove innovation and gradually reduced costs. Earth observation satellites also found commercial applications beyond their original scientific purposes. Companies recognized that the imagery collected from orbit had monetary value for various industries. Agricultural businesses wanted to monitor crop health across vast farmlands. Energy companies sought to identify promising geological formations for oil and gas exploration. Urban planners needed current information about land use and development patterns. A commercial market for satellite imagery developed, with companies operating their own Earth observation satellites and selling the resulting images to customers who could extract useful business intelligence from orbital perspectives. The French Spot satellite system, inaugurated in 1986, exemplified this commercial approach to Earth observation. While operated by a government space agency, Spot was explicitly designed to generate revenue by selling its imagery on the commercial market. The satellite's high-resolution cameras captured detailed views of Earth's surface that businesses and governments purchased for planning and analysis. This commercial model demonstrated that Earth observation could be financially self-sustaining rather than perpetually dependent on government funding. Insurance companies entered the satellite business from an entirely different angle, developing specialized space insurance policies that covered the substantial risks of launch failures and orbital malfunctions. The premiums for these policies reflected the genuine dangers involved in reaching and operating in space, where a single error or unexpected event could destroy hundreds of millions of dollars worth of hardware. As the satellite industry matured, insurers accumulated enough data to assess risks more accurately, and a sophisticated market for space insurance emerged alongside the satellite operations it protected. The regulatory landscape evolved to accommodate this growing commercial presence in space. Governments had to allocate radio frequencies to prevent satellites from interfering with each other's transmissions. Orbital slots for geostationary satellites became valuable real property, with international agreements dividing the geostationary belt among nations who could then license these positions to commercial operators. The process of obtaining licenses, frequencies, and orbital assignments became its own specialized field, requiring legal and technical expertise to navigate the complex international frameworks. By the 1990s, satellite manufacturing and operations had become a mature industry, generating billions of dollars in annual revenue. Companies specialized in different aspects of the business. Some focused on building satellites, others on launching them, still others on operating communication networks or selling Earth observation data. The industry supported thousands of highly skilled jobs in engineering, manufacturing, operations, and business services. Universities developed programs specifically designed to train the satellite industry's workforce, recognizing this sector as a permanent feature of the economic landscape. The cellular telephone revolution that swept across the world created yet another commercial opportunity. Several companies developed plans for satellite telephone systems that would provide mobile communication anywhere on Earth, including oceans and remote areas beyond the reach of ground-based cellular towers. These systems required dozens of satellites working in coordination, representing investments of billions of dollars with uncertain returns. Some of these ambitious ventures succeeded while others struggled, but they pushed the boundaries of what commercial satellite networks could achieve. As commercial satellite operations flourished, they became deeply woven into the fabric of daily life in ways most people never consciously noticed. Credit card transactions flowing through satellite links, television programs delivered from space, ships navigating by orbital signals, weather forecasts based on satellite data. All these services operated invisibly in the background of modern civilization. The satellite business had achieved something remarkable. It had made space operations routine, even ordinary, transforming the extraordinary achievement of placing hardware in orbit into just another utility service supporting human activity on the ground below. This commercial expansion meant that more eyes watched Earth from above, more communication channels connected distant places, and more resources flowed toward improving and expanding orbital capabilities. The business of satellites had become self-perpetuating, generating the revenue to fund its own growth and innovation. Where government programs had opened the door to space, commercial enterprise was building entire cities beyond that threshold, constructing an orbital economy that would only grow more significant with passing years. As commercial ventures expanded their reach into orbit, another realm of satellite development had been proceeding quietly. largely hidden from public view. While television signals bounced across continents and weather patterns revealed themselves in swirling cloud formations, other satellites were being designed with different purposes entirely. These spacecraft would carry cameras pointed not toward the stars or the weather, but down toward the surface of Earth itself, gathering information that governments considered vital to their security. The concept of reconnaissance from above was far from new. Military commanders had climbed hills and towers for centuries to observe enemy positions, and by the American Civil War, observers were ascending in balloons tethered above battlefields, sketching what they saw below. When aircraft arrived in the early 20th century, aerial photography became an essential tool, with increasingly sophisticated cameras capturing details from ever greater heights. Yet even the highest flying aircraft had limitations. They needed nearby bases, they could be intercepted, and they could only cover so much territory in a single mission. Satellites offered something unprecedented: the ability to observe any location on Earth from the sanctuary of space, beyond the reach of conventional defenses. The same orbital mechanics that allowed weather satellites to sweep across the globe would work just as effectively for cameras designed to photograph military installations, naval vessels, and industrial complexes. The first photographic reconnaissance satellites emerged during the late 1950s, products of intense Cold War competition. The Corona program, initiated by the United States in February 1959, represented a remarkable feat of engineering hidden behind cover stories about scientific research. These satellites carried powerful cameras and long strips of film, much like the equipment used in high-altitude spy planes, but adapted for the harsh environment of space. The mechanics of these early reconnaissance satellites involved fascinating technical challenges. Unlike communications satellites that could transmit their data immediately via radio signals, photographic satellites of that era had no way to send their images to Earth electronically with sufficient quality. Instead, after several days of photographing targets below, the satellite would eject a capsule containing the exposed film. This capsule would descend through the atmosphere protected by a heat shield, deploy a parachute, and then be snagged mid-air by specially equipped aircraft trailing capture lines. The entire process resembled something from an adventure novel, yet it became routine operation over many years. The resolution of these camera systems steadily improved. Early Corona satellites could distinguish objects a few dozen feet across, but successive generations achieved increasingly fine detail. Engineers developed specialized optical systems, designing lenses that could focus through hundreds of miles of space and atmosphere to capture clear images of targets on the ground below. The film itself had to withstand the temperature extremes and vacuum of space while remaining capable of recording high-quality photographs. Beyond visual imaging, other reconnaissance satellites monitored radio communications and electronic signals. These spacecraft carried antennas and receivers designed to intercept broadcasts, radar emissions, and other electromagnetic transmissions. Orbiting above Earth's surface, such satellites could eavesdrop on communications across vast territories, collecting signals that provided insight into military activities, technological capabilities, and strategic intentions. Early warning satellites represented another category of orbital sentinel. These spacecraft watched for the bright infrared signatures of missile launches, providing crucial minutes of advance notice that would allow defensive responses. Positioned in high geostationary orbits, where they could continuously monitor large portions of Earth's surface. These satellites carried sensitive infrared detectors that could distinguish the intense heat of rocket exhaust against the cooler background of Earth below. The technical sophistication of these systems increased dramatically over decades. Film capsules eventually gave way to digital imaging systems that could transmit photographs electronically, eliminating the dramatic mid-air recoveries, but allowing near instant delivery of images to ground stations. Synthetic aperture radar enabled satellites to see through clouds and darkness, using radio waves instead of visible light to create detailed images regardless of weather or time of day. The presence of reconnaissance satellites changed international relations in subtle but significant ways. Both sides in the Cold War came to accept satellite observation as preferable to more risky forms of intelligence gathering. Unlike aircraft that might be shot down or agents who might be captured, satellites operated in space where their presence, while known, could be tolerated without direct confrontation. This mutual surveillance actually contributed to stability by reducing uncertainty about the other side's military capabilities and intentions. Treaties gradually emerged to govern military activities in space. The Outer Space Treaty of 1967 prohibited placing weapons of mass destruction in orbit, but notably allowed reconnaissance satellites to continue operating. The transparency provided by these orbital observers arguably supported arms control efforts, as parties to various treaties could verify compliance through their own satellite observations rather than relying solely on trust. As digital technology advanced, the capabilities of imaging satellites expanded beyond what early designers might have imagined. Modern reconnaissance satellites can capture images with remarkable detail, tracking changes in facilities over time, monitoring naval deployments, and observing activities in remote regions. Multiple types of sensors provide complementary information, with some satellites carrying both optical cameras and radar systems, others monitoring infrared signatures or intercepting communications across numerous frequency bands. The network of reconnaissance satellites eventually grew to include contributions from various nations. Countries beyond the superpowers developed their own observation capabilities, launching satellites to monitor their own security concerns and regional interests. Commercial satellite imagery companies also emerged, offering photographs of Earth's surface to any customer willing to pay, though generally at lower resolution than classified military systems. These orbital sentinels continue their silent watch, passing overhead multiple times each day, their cameras and sensors gathering information that informs decisions in government centers around the world. The spacecraft themselves remain engineering marvels, combining optical systems, sophisticated sensors, guidance systems, and communication equipment into packages that can function reliably in the harsh environment of space for years or even decades. As this realm of satellite activity expanded, touching matters of security and intelligence, the parallel development of satellites for scientific Earth observation was also flourishing. While reconnaissance satellites looked down with specific strategic interests, another generation of spacecraft would monitor our planet's climate, oceans, and atmosphere with equally sophisticated sensors, but different purposes entirely. As military satellites continued their classified watch from orbit, another family of observational platforms began turning their sophisticated instruments toward Earth itself, not for strategic purposes, but to understand the living, breathing planet beneath them. These modern Earth observation satellites represent some of humanity's most advanced technological achievements, their sensors reading the invisible signatures of our world's complex systems with remarkable precision. The story of contemporary Earth observation truly gained momentum in the late 1990s and early 2000s as satellite technology matured and our questions about planetary processes grew more sophisticated. While earlier satellites like Landsat had shown what was possible, a new generation of instruments could detect phenomena far beyond what human eyes could see. These satellites became our planetary physicians, taking Earth's vital signs day after day, year after year, creating an unbroken medical record of our world's health. Consider the Terra satellite, launched by NASA on December 18, 1999, as the new millennium approached. This massive observatory, weighing nearly 5 tons, carried 5 separate instruments, each designed to study different aspects of Earth's interconnected systems. One instrument measured the energy balance between incoming sunlight and outgoing heat. Another tracked clouds and particles suspended in the atmosphere. A third mapped land surface features and temperatures. Together, these sensors worked in concert, painting a comprehensive picture of how Earth's atmosphere, oceans, and land surfaces interact. Terra circles Earth in a polar orbit, passing over the same locations at the same local time each day, creating consistent lighting conditions for its observations. This sun-synchronous orbit crosses the equator each morning at around 10:30, when shadows cast by the sun help reveal terrain details, while sunlight remains bright enough for clear imaging. The satellite completes more than 14 orbits daily, its instruments continuously recording data that streams down to receiving stations scattered across the globe. Following Terra came Aqua in 2002, a sister satellite crossing the equator each afternoon, providing complementary observations at a different time of day. Aqua's name reflects its focus on Earth's water cycle, tracking moisture as it evaporates from oceans, forms clouds, falls as precipitation, and flows back to the seas. 6 instruments aboard Aqua measure everything from sea surface temperatures to humidity levels at different atmospheric heights, building 3-dimensional maps of how water moves through our planet's systems. These satellites observe Earth in wavelengths far beyond visible light. Infrared sensors detect heat, revealing ocean temperatures and identifying areas where volcanic activity warms the ground. Microwave instruments peer through clouds that would blind optical cameras, measuring soil moisture and tracking storms even in darkness. Ultraviolet sensors monitor the ozone layer, watching protective gases that shield life from harmful solar radiation. Each wavelength tells a different story, and together they create a rich narrative of planetary processes. The European Space Agency contributed its own remarkable observer in 2002 with Envisat, at the time the largest Earth observation satellite ever built. Envisat carried 10 instruments weighing 2 tons, including advanced radar systems that could map subtle changes in land elevation. These radar measurements revealed how Earth's surface rises and falls, detecting the slow creep of glaciers, the subsidence of land over depleted aquifers, and even the gentle bulging of volcanoes as magma moves beneath them. Radar satellites brought another advantage beyond seeing through clouds. By comparing images taken at different times, scientists could detect changes measured in mere centimeters. This technique, called interferometry, transformed our ability to study earthquakes, landslides, and ice sheet dynamics. The ground itself became legible in new ways, its movements tracked with unprecedented precision from hundreds of kilometers above. Ocean-watching satellites added their own specialized capabilities. Jason Y1, launched in 2001, carried altimeters that measured sea surface height to within a few centimeters by timing how long radar pulses took to bounce back from the waves below. These measurements revealed the subtle hills and valleys in ocean surfaces created by currents, temperatures, and salinity differences. Year after year of altimeter data showed how sea levels respond to changing climate, providing crucial measurements of planetary change. Other satellites focused on atmospheric composition, measuring trace gases that affect climate and air quality. The Aura satellite, joining its siblings in 2004, carried instruments that map pollutants, greenhouse gases, and ozone with remarkable detail. Its measurements revealed how human activities, natural processes, and atmospheric chemistry interact in complex ways. Scientists could watch pollution plumes drift across continents, track methane emissions from wetlands and industrial sites, and observe how forest fires inject particles high into the atmosphere. Geostationary satellites also evolved far beyond their early weather-watching roles. The GOES series, operated by the United States, and similar systems run by Europe, Japan, India, and other nations, now carry sophisticated sensors that update their views every few minutes. These constant observers watch storms develop, track wildfires as they spread, and monitor atmospheric conditions with temporal resolution, impossible for polar orbiting satellites that pass over each location only twice daily. Modern Earth observation satellites collaborate across borders and agencies. The International Charter on Space and Major Disasters, established in 2000, coordinates satellite observations during emergencies. When earthquakes strike, hurricanes approach, or floods threaten, member agencies redirect their satellites to capture images of affected areas, providing critical information to rescue workers and relief organizations. Space-based eyes help save lives by revealing where help is needed most. The Sentinel satellites, launched by Europe starting in 2014, created a new kind of observational system. Rather than single platforms carrying many instruments, the Sentinel program deployed multiple specialized satellites working together. Sentinel-1 carries radar for all-weather imaging. Sentinel-2 captures high-resolution optical images. Sentinel-3 measures ocean and land temperatures. Sentinel-5P tracks air quality. Together, they provide freely available data to anyone who wants to understand our changing planet. This democratization of Earth observation data has transformed research. Scientists worldwide access satellite measurements to study local environments, track deforestation, monitor crop health, map urban growth, and investigate countless other phenomena. What was once restricted information available only to governments has become a global resource for understanding planetary change. The data flowing from these satellites accumulates into archives stretching back decades, creating time-lapse views of Earth's transformation. Ice sheets grow and shrink. Forests expand or disappear. Cities spread across landscapes. Lakes fill or dry. Coastlines shift. These long-term records reveal trends invisible to observers on the ground. showing how Earth responds to natural cycles and human activities over years and decades. As these modern observers continue their patient watch, they write a detailed biography of our planet during this particular moment in its long history. Their instruments measure, their transmitters send, and their data archives grow, creating an unprecedented record of Earth as it is now, a baseline against which all future changes will be measured. Orbiting silently above, they keep vigil over the world below, their sensors reading stories written in heat and light, and the invisible dance of molecules in the air. As the 21st century dawned, a revolution was quietly taking shape in the world of satellites, one that would transform who could reach space and what could be accomplished there. For decades, satellites had been massive, expensive machines, each one costing hundreds of millions of dollars and requiring years of development. These giants of orbital technology were accessible only to wealthy nations and major corporations with deep pockets. But change was coming, carried on the wings of smaller and smaller spacecraft. The story of miniaturization began, as many space innovations do, with a simple but powerful idea. In 1999, professors at California Polytechnic State University and Stanford University proposed a new standard for small satellites. They called them CubeSats, and each one would measure just 10 centimeters on each side, forming a perfect cube about the size of a Rubik's puzzle. These tiny spacecraft would weigh no more than 1 kilogram, making them featherweights compared to the multi-ton satellites that had dominated space for 40 years. The genius of the CubeSat concept lay not just in its small size, but in its standardization. By creating specific dimensions and interfaces, the professors made it possible for these miniature satellites to hitch rides to orbit aboard rockets launching larger payloads. Multiple CubeSats could nestle together in special deployers, taking advantage of spare capacity on launches headed to space anyway. This approach dramatically reduced the cost barrier to reaching orbit. Universities embraced this opportunity with enthusiasm. Students who had only dreamed of working on space missions found themselves building actual satellites in campus laboratories. The first CubeSat reached orbit in 2003, launched from Russia. These pioneers were simple by satellite standards, but they represented something profound. Space access was beginning to democratize. As the years passed, CubeSats grew more sophisticated. Engineers discovered that 1-unit cubes could be combined into larger configurations. 2-unit, 3-unit, and even 12-unit CubeSats emerged, still following the basic 10-centimeter standard, but offering more room for instruments, power systems, and communications equipment. What had begun as educational tools evolved into capable scientific platforms. The commercial world took notice. Startup companies recognized that small satellites could accomplish tasks that once required massive spacecraft. Planet Labs, founded in 2010, pioneered the use of CubeSat constellations for Earth imaging. Rather than building one large, expensive imaging satellite, they launched flocks of small ones, each carrying capable cameras despite their compact size. This approach offered a revolutionary advantage. If one satellite failed, dozens of others remained operational, and new ones could be launched quickly and affordably to replace losses. By 2013, Planet Labs had deployed their first constellation of imaging satellites, which they called doves. These peaceful-sounding spacecraft, each about the size of a shoebox, began photographing Earth's entire land surface daily. The frequency and coverage surpassed what traditional satellites could achieve. Farmers used the imagery to monitor crop health. Conservationists tracked deforestation. Urban planners watched cities grow and change. All of this became possible because small satellites made frequent, comprehensive Earth observation economically viable. Other companies pursued different visions, enabled by miniaturization. Spire Global built constellations of small satellites to track ships at sea and monitor weather patterns by measuring how GPS signals bent through the atmosphere. Their satellites, no larger than a loaf of bread, could detect temperature, pressure, and humidity at different altitudes, contributing valuable data to weather forecasting models worldwide. The miniaturization trend extended beyond CubeSats to somewhat larger spacecraft, still dramatically smaller than traditional satellites. Companies began designing satellites weighing tens or hundreds of kilograms rather than tons, optimized for efficient manufacturing and rapid deployment. These platforms occupied a middle ground, larger than CubeSats, but far more compact and affordable than conventional satellites. Perhaps the most ambitious application of small satellite technology emerged in plans for mega constellations designed to provide internet connectivity across the globe. Companies like OneWeb and SpaceX announced intentions to launch thousands of satellites into low Earth orbit, creating networks that could beam internet signals to even the most remote locations on the planet. Each satellite in these constellations would be relatively small and built using mass production techniques borrowed from consumer electronics manufacturing. SpaceX's Starlink constellation began deployment in 2019 with satellites weighing about 260 kilograms each. Though larger than CubeSats, these spacecraft represented a new paradigm in satellite design, built for low cost and high volume production. The company launched them in batches of 60 at a time aboard their own Falcon 9 rockets, with plans for eventual constellations numbering in the thousands. This scaling of satellite numbers brought new capabilities, but also new responsibilities. The very success of small satellites raised questions about orbital crowding that would need addressing, but the fundamental achievement remained clear. Space access had transformed from an exclusive domain into something approaching accessibility. Developing nations gained opportunities to establish space programs without investing billions in infrastructure. Kenya, the Philippines, and many other countries launched their first satellites using CubeSat technology. These missions serve practical purposes like environmental monitoring and communications, while also training a new generation of engineers and scientists in space technology. The technical achievements packed into these small packages proved remarkable. Engineers developed miniature versions of systems that once required entire satellite buses. Tiny reaction wheels provided attitude control. Compact solar panels and efficient batteries supplied power. Sophisticated radios maintained communications across the vastness of space. Cameras, spectrometers, and other instruments delivered scientific data despite their diminutive size. Each advancement in miniaturization opened new possibilities. Private space stations and orbital platforms began incorporating small satellite deployment capabilities. Astronauts aboard the International Space Station hand-launched CubeSats from the Japanese airlock, giving these tiny spacecraft a gentle push into their own orbits. The image of an astronaut releasing a small satellite into the darkness became a symbol of space's evolving accessibility. Universities continued pushing boundaries with increasingly ambitious CubeSat missions. Some ventured beyond Earth orbit to test technologies for deep space exploration. Others demonstrated new propulsion systems, advanced communications techniques, or novel scientific instruments. Student teams that built and operated these missions graduated with practical experience in spacecraft design, launch operations, and orbital management, ready to lead the next generation of space endeavors. The small satellite revolution also sparked innovation in launch services. Companies developed small rockets specifically designed to carry these lighter payloads, offering dedicated launches instead of rideshare arrangements. This specialization created yet another layer of accessibility, allowing satellite operators to choose specific orbits and launch times rather than accepting whatever secondary payload opportunities arose. As night settles and these small satellites pass overhead, invisible to the naked eye but diligently performing their missions, they represent a fundamental shift in humanity's relationship with space. The orbital realm that once belonged exclusively to superpowers and major corporations now welcomes contributions from students, startups, and nations taking their first steps beyond Earth's atmosphere. The revolution of small satellites proved that reaching space required not just massive rockets and enormous budgets, but also clever engineering, standardization, and the courage to think differently about how we build and deploy the tools of orbital technology. As the population of satellites grew from dozens to hundreds, and then to thousands, the space around Earth began to resemble something quite different from the empty void early pioneers had imagined. The orbital environment, once pristine and open, became increasingly crowded with both functioning satellites and the remnants of decades of space activity. This transformation brought new responsibilities and challenges that required international attention and cooperation. By the early 21st century, tracking systems maintained by various space agencies monitored more than 20,000 objects larger than a softball circling Earth. These included active satellites performing their intended missions, retired satellites that had completed their service, spent rocket stages that had delivered payloads to orbit, and fragments created by accidental collisions and deliberate destructions. Each object, regardless of size, traveled at tremendous speeds, with velocities in low Earth orbit reaching approximately 17,000 miles per hour. At such speeds, even a paint fleck could damage a functioning satellite, while larger debris posed risks of catastrophic collisions. The United States Space Surveillance Network, using a combination of ground-based radars and optical telescopes, continuously tracked these orbital objects, updating a catalogue that had grown steadily since the beginning of the space age. Similar tracking capabilities were developed by Russia, Europe, and other spacefaring nations. These systems scanned the sky day and night, measuring positions and trajectories, calculating orbits, and predicting where thousands of objects would be hours and days into the future. The mathematical complexity of this undertaking was considerable, as each object followed its own elliptical path, influenced by Earth's gravitational variations, atmospheric drag, solar radiation pressure, and the gentle tugs of the moon and sun. For operators of active satellites, collision avoidance became a regular concern when tracking data indicated that two objects might pass uncomfortably close to each other. Operators face decisions about whether to maneuver their spacecraft. These conjunction assessments happened frequently, sometimes several times per week, for satellites in particularly crowded orbital regions. Moving a satellite required careful planning, as thruster firings consumed precious fuel that satellites carried in limited quantities. Each maneuver needed to move the satellite far enough to ensure safety, while conserving fuel for future operations and eventual controlled deorbit at mission's end. The International Space Station, with its large size and occupied status, received particularly careful attention. Mission control teams regularly screened for potential conjunctions, and the station performed debris avoidance maneuvers multiple times each year when objects were predicted to pass too close. Astronauts aboard sometimes moved into their Soyuz spacecraft as a precautionary measure when smaller debris pieces approached with insufficient warning time for station maneuvers. These moments reminded crews that their home in orbit existed within an environment requiring constant vigilance. The problem of orbital debris intensified dramatically when operational satellites suffered catastrophic failures. In February 2009, an active American communications satellite and a defunct Russian military satellite collided above Siberia at an altitude of nearly 500 miles. The impact created thousands of trackable fragments and countless smaller pieces, instantly increasing the debris population in one of the most heavily used orbital zones. This collision, the first accidental hypervelocity impact between two intact satellites, demonstrated that the debris problem could worsen through cascading events, where collisions created fragments that caused additional collisions. Scientists had theorized about this possibility for decades. Donald Kessler, a NASA researcher, had described in the late 1970s how debris populations could reach densities where collisions became self-sustaining, creating an ever-expanding cloud of fragments, regardless of whether new satellites were launched. This scenario, often called the Kessler syndrome, represented a troubling possibility where certain orbital regions might become unusable for generations. Mathematical models suggested that some altitude bands had already reached or were approaching critical densities where this cascade effect could begin. In response to growing concerns, the international community developed guidelines and standards for responsible orbital operations. The Interagency Space Debris Coordination Committee, formed in 1993, brought together major space agencies to share research and develop mitigation practices. These guidelines recommended that satellites in low Earth orbit should be designed to re-enter the atmosphere within 25 years after mission completion, either through natural orbital decay or controlled deorbit. For satellites in higher orbits where atmospheric drag was negligible, guidelines suggested moving defunct spacecraft into graveyard orbits away from operational zones. Engineers began designing satellites with debris mitigation in mind. This meant including features like passivation systems that vented remaining fuel and discharged batteries at mission end, preventing explosions that had historically created much debris. Designers also worked to minimize the creation of small particles during normal operations, capturing paint flakes and other materials that might otherwise shed into orbit. Launch vehicle operators developed techniques to deorbit spent rocket stages rather than leaving them in orbit indefinitely. The challenge of removing existing debris spurred creative thinking. Researchers proposed various concepts for active debris removal, from robotic spacecraft that could grab defunct satellites to nets, harpoons, and laser systems that might nudge objects toward re-entry. Several experimental missions tested technologies for approaching and capturing uncontrolled objects in orbit, demonstrating the technical complexity of rendezvousing with tumbling debris pieces. The economics of debris removal remain challenging, as the cost of removing even a single large object exceeded typical satellite launch costs, and thousands of hazardous objects orbited overhead. Ground-based tracking systems continued improving their capabilities, using more powerful radars and sensitive optical systems to detect smaller objects and track them more precisely. Better tracking meant better predictions of conjunctions and improved understanding of the debris environment. Some systems could track objects as small as a few inches across, though millions of smaller fragments remained undetectable with current technology, invisible threats that satellites simply had to accept as background risk. International cooperation in sharing tracking data became increasingly important as more nations and commercial entities operated satellites. The challenge of maintaining a sustainable orbital environment belonged to no single nation, but required collective effort. Forums for discussion brought together government agencies, commercial operators and researchers to address common concerns. While orbital space remained legally accessible to all under the Outer Space Treaty of 1967, the practical reality of growing congestion demanded coordination and voluntary adherence to debris mitigation practices. As small satellite constellations proliferated, with some companies planning to launch thousands of satellites into coordinated networks, questions about orbital sustainability gained urgency. These mega constellations promised global connectivity, but also meant placing unprecedented numbers of satellites in already crowded orbital zones. Operators of these systems emphasized their commitment to debris mitigation, incorporating design features for controlled deorbit and demonstrating removal capabilities. Yet the scale of deployment represented a significant change in orbital population dynamics. The challenges in orbit reflected humanity's growing presence in space and the need for stewardship of this environment. The same ingenuity that had enabled the satellite age now turned toward ensuring that orbital space remained usable for future generations, balancing continued access with long-term sustainability as the community of spacefaring nations worked to preserve the frontier above. As we've traced the journey of satellites from dreams to debris management, we now turn our gaze toward the horizon, where new possibilities shimmer like stars waiting to be discovered. The story of satellites continues to unfold above us, written in the silent paths of objects yet to be launched, technologies still taking shape in laboratories, and applications not yet imagined by those who will one day depend upon them. The satellites of tomorrow are already taking form in research facilities across the world. Engineers are developing sensors far more sophisticated than those currently in orbit, instruments capable of detecting subtle changes in Earth's atmosphere, oceans, and land surfaces with remarkable precision. These next-generation observation platforms will measure atmospheric composition down to individual molecules, track ocean currents at depths previously invisible from space, and monitor vegetation health with such accuracy that farmers might receive information about specific sections of their fields. The data flowing from these advanced satellites will arrive not in delayed batches, but in near real-time streams, allowing rapid responses to emerging conditions. Propulsion systems for satellites are evolving beyond the traditional chemical thrusters that have maneuvered spacecraft for decades. Electric propulsion systems, which use electricity to accelerate ions to high velocities, offer far greater efficiency for moving satellites and maintaining their positions. Some experimental designs explore solar sails that catch the gentle pressure of sunlight itself, pushing spacecraft along without consuming any fuel at all. These innovations promise satellites that can operate longer, travel farther, and adjust their orbits more flexibly than their predecessors. Communication satellite technology continues advancing toward higher frequencies and greater bandwidth. Satellites operating in the K-band and even higher frequencies can transmit vastly more data than earlier systems, though they face greater challenges from weather interference. Laser communication systems, which send information on beams of light rather than radio waves, are moving from experimental demonstrations toward operational deployment. These optical links can carry enormous amounts of data between satellites and ground stations, enabling applications that would overwhelm conventional radio systems. The concept of satellite servicing is emerging from theory into practice. Just as the Hubble Space Telescope benefited from astronaut repair missions, future satellites might be maintained, refueled, and upgraded by robotic servicing spacecraft. These mechanical attendants could extend satellite lifespans by replacing failed components, top off fuel tanks, or even relocate satellites to new orbits. Several demonstration missions have already tested the technologies needed for such operations, grasping satellites in orbit and proving that orbital mechanics allow such delicate rendezvous. Manufacturing in space presents possibilities that seem almost like science fiction returning full circle. The microgravity environment of orbit allows processes impossible on Earth's surface, from growing unusual crystal structures to producing certain types of fiber optics with exceptional purity. Small manufacturing satellites have already demonstrated some of these techniques, and larger platforms may follow. Some visionaries imagine satellites that could use materials from asteroids, though such capabilities remain distant prospects requiring technologies still in early development. Satellite constellations are expanding in ambition and scale. While existing networks coordinate dozens or hundreds of satellites, proposed systems envision thousands of small satellites working together to provide services ranging from global internet access to continuous Earth monitoring. These mega constellations promise to bring connectivity to remote regions that terrestrial infrastructure cannot easily reach, though they also amplify challenges of space traffic management and orbital debris that we've worked to address. Power generation for satellites is advancing beyond the solar panels that have energized spacecraft since the earliest days. While photovoltaic technology continues improving in efficiency, some researchers explore alternatives for specialized applications. Nuclear power sources, long used for deep space missions beyond the reach of adequate sunlight, might find new applications in satellites requiring more power than solar panels can practically provide. Advanced battery technologies promise better energy storage for eclipse periods when satellites pass through Earth's shadow. The integration of artificial intelligence and autonomous systems will transform how satellites operate. Rather than waiting for instructions from ground controllers, satellites equipped with sophisticated onboard processing could analyze their own sensor data, identify significant events, and respond appropriately without human intervention. Earth observation satellites might recognize developing weather systems, agricultural stress, or environmental changes, and automatically focus their instruments for detailed study. Navigation satellites could monitor their own health and coordinate with constellation partners to maintain optimal service. International cooperation in satellite development appears likely to expand, building on successful collaborative projects that have demonstrated the benefits of shared resources and expertise. Joint missions combine the capabilities of different space agencies, spreading costs while advancing science and technology. Satellites developed through international partnerships can serve multiple regions simultaneously, and the technical standards they establish help ensure compatibility across different systems. The commercialization of satellite technology continues accelerating. Companies are investing in satellite systems for applications ranging from tracking shipping containers to monitoring industrial facilities for environmental compliance. Private satellite operators are launching imaging systems with resolution fine enough to distinguish individual objects, offering this data commercially to customers ranging from agricultural businesses to urban planners. This commercial sector brings innovation and efficiency, though it also requires thoughtful regulation to balance business interests with public concerns. Looking further ahead, some concepts push the boundaries of current engineering. Satellites assembled in orbit from components launched separately could grow larger than any structure that fits within current rocket fairings. Solar power satellites that collect energy in space and beam it to Earth have been studied for decades, though formidable technical and economic challenges remain before such systems could become practical. Space-based telescopes, even more capable than Hubble, wait in planning stages, promising views of the universe that will make our current observations seem like glimpses through frosted glass. As satellite capabilities expand, questions about sustainability become increasingly important. The orbital environment is not infinite, and the valuable regions closest to Earth can accommodate only so many satellites before congestion becomes problematic. Future satellite systems will need to incorporate end-of-life planning from their initial design, ensuring they can be safely deorbited or moved to disposal orbits when their missions conclude. Technologies for removing existing debris may become necessary to preserve access to space for future generations. The satellites yet to come will continue the transformation that began when Sputnik's radio signal first beeped across the world. They will extend human capabilities in ways we can anticipate and others we cannot yet imagine. They will carry instruments we are still perfecting and operate through principles we are still discovering. Above us, in the vast arena of orbital space, the future is taking shape, one satellite at a time, writing the next chapters in a story that shows no sign of ending, but rather keeps expanding outward, upward, into possibilities as boundless as the space through which these remarkable machines travel. As we bring to a close our journey through the remarkable story of satellites, from those early dreams of artificial moons to the sophisticated networks that now circle our planet, we hope these quiet tales of human ingenuity and cosmic wonder have gently carried you toward rest. Thank you for joining us on this peaceful exploration among the stars. If these calm adventures have brought you comfort, we'd love to have you with us again. Like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way here. And now, as the night deepens and your mind settles like satellites finding their orbit, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.